All right. Good morning, everyone. Hi. Welcome to the second day. How are you? Exactly. All right. So I'm Stefan. Hi. I will be the host for today, together with Matthias Endler in this room. A couple of house rules and logistics, basically the same as last day. If you have any need at all the people in the yellow shirts are here to help you. It's a huge crowd of volunteers and organizers. They are running around everywhere. It's amazing. So if you have anything, ask them when you need.
Up in an arc and return it. Why did we wrap it in an arc? I'll explain that in a second. Rune approaches script isolation differently than some of the other languages. It lets us create a virtual machine for each thing we wish to run in isolation. For our purposes, and because in most cases so far we did this either explicitly or implicitly, we'll want an isolated run for each greeting. So we create a new virtual machine based on the runtime and the unit we have. And that's why they are both arcs, so that cloning them is cheap and they can be shared. We then execute the greet function with our who argument, then wait for completion because Rune is an async first language. Then we attempt to construct a string from that return value and return it. And that's up to WebAssembly memory, then pick out the string from said location and a whole lot of boilerplate, and even with this big string behind me it wouldn't fit. Honorable mention only. In the repository linked to at the end of this talk, there will be a WebAssembly example, but something to get started with. There's another bonus language I left here, which I need to mention, Rust itself. It's kind of. So there's a way to have an owned object on, but not clone it into the script side. You can build accessors. So you make a kind of object available to the scripting side. And instead of having direct access to the hash map, you implement accessors. That means that you still need an owned thing on the Rust side, usually. But you don't need to clone it for the script too. I ran into. So I don't have a solution for you.
All right, but you did say the keyword accessors. Thank you.
You're welcome.
Thank you very much. I see there are more questions in the audience. I'm sure Algernon will be here for longer to answer them during the hallway track. And with that, after the first block. So we now have a coffee break until 11:40. There are snacks downstairs, coffee, some water and juice. So refresh yourselves, have some chat with folks. See you back at 11:40.
We'll bust this myth with measurements, not just vibes. So what is fast enough? Fast enough is subjective. It's anchored to experience. So let's ask someone. My experience with JavaScript is, yeah, it's fast enough for the workloads I care about. Wait, isn't this pain points?
Yes. It's too good to be true. There have to be pain points. But they're all solvable with some user land considerations, and they also all have really exciting work going on to get to resolve them. So the first pain point is that your WebAssembly module has to be completely valid for the browser it's running on, or it fails. And this can get a little tricky with target features. We had a case where a dependency crate had a target features for SIMD. We were trying to build a scalar build, and so there were SIMD instructions leaking into our binary, and it could crash. This is not memory leaks as in memory leaks, but it's more like the concept of memory leaking into your JavaScript APIs. Because there is linear memory being allocated, and the JavaScript APIs have to deal with it. There's many tools for that, but you can have an explicit free. There's a finalization registry that lets you run a callback when the garbage collection runs. Allows automatic freeing of memory. So there's ways to work around this. There are also not that many tools yet available for lazy loading or dynamically loading pieces of the Wasm binary together. There's some very promising work with Wasm split, and there's also some really cool work with Dioxys and Leptos and other lazy. The error strategy is up to you. What happens if there's a panic? Grows to the linear memory. It's up to you. And finally, there is a dependence on third-party crates like Wasm BindGen, which is great, but there are some things that aren't representable in just Rust compiling to the extern ref. There's really opaque.
Yeah. Thank you everyone for listening. In today's talk, we went over some Rust and WebAssembly background. We spoke about Rust and WebAssembly characteristics, how to design your FFI to get optimal performance when you need it. We ended with some pain points. If you want to learn more, this is the site we mentioned. It references all the benchmarks that we talked about in this talk. For listening.
Thank you very much, Touch and Andrew. That was a lot of questions, but we only have a few minutes left. So go ahead quick. We will walk the mic around physically. Too late.
Thank you very much for the very good talk. You touched upon this a tiny bit in the end, but one thing I always run into with WebAssembly is that error handling just feels very kind of difficult. Do you have any your work at Canva on how to do error handling across this boundary from Wasm to JavaScript?
It's a hard problem. It's certainly a pain point. At some point in time, we explored returning error codes across the FFI. But that obviously, yeah, if you need to return more, then if you need to return something, then you need to create a struct, and that struct has an error code and the thing that you actually want to return, which is not ideal either. So nothing great, to be honest.
So in the end, you moved away from this error code approach again?
We try catch. Okay. But WebAssembly itself has the ability to have multi-value return types. But that, and if that that's probably the best outcome, but we just can't use it right now.
Okay, thank you.
Hi, thanks for a great talk, first of all. I just need a quick comment on the performance gap slide you heard early on. That's not a widening performance gap. iPhones have been 10 times faster and it's still 10 times faster. You need to do, a division, not a subtraction to compare performance over time. Sorry, I just couldn't let. My main comment is, so it seems like you're doing a lot of small calls from assembly. Is that correct? As opposed to like calling once and having the WebAssembly run for forever. Is this because you have like a lot of JavaScript code that you're planning on porting over to WebAssembly, or do you feel like there's a place for JavaScript and there's a place for Rust, and they need interface often?
So Canva has, we have several thousand engineers who are well versed in JavaScript. And so we need to provide an API for them to use without requiring thousands of engineers to learn Rust. And so our use of Rust and WebAssembly is JavaScript making thousands of calls into WebAssembly for any given interaction. Yeah.
Okay, yeah, that makes sense. Thank you.
Thank you very much for the talk. I was wondering, besides using WebAssembly in the browser, as you mentioned at the beginning, WebAssembly can also very nicely be used on other architectures, for example, because of its sandboxing or other properties. Do you actually do that, or do you only assembly in combination with JavaScript?
I think yes. The answer is yes, basically. Yes, I think Rust provides something very portable. We haven't explored using WebAssembly in the backend. We just directly compile to that target.
Thank you.
We have time for one more.
Hi, thank you for the presentation. It was great. One question I wanted to ask is around async compatibility with WebAssembly. Do you think there's a future for Wasm supporting async runtime?
Oh, that is a really interesting question. I'm not sure. I don't know. The only thing I have in now it really nicely makes async Rust work in a JavaScript runtime, leveraging the JavaScript like async execution model. But I can't comment on the WebAssembly.
Thank you.
So, thank you very much. That was Andrew Jakubovic and Touch Pereira.
Thank you. Thank you.
As for our next talk, which will start in a few minutes, time to switch rooms now. It will be by Mordecai Emmanuel Itukuru. It will be a remote talk. We will have a few minutes to do the setup, and we see you back in a bit. Welcome back from our break. We will jump right into our next talk. I wish I had more time to maybe say a little Rust joke. I had one about macros, but unfortunately I don't have time to expand on it. Our next Mordecai Emmanuel Etokuro. It will be a remote talk. Mordecai is working and is interested in education and Rust, which is a super interesting combination. He promotes the adoption of Rust at African universities, and he's a project team lead at Rustaceans Africa. Give it up for Mordecai.
Okay, everyone. It's quite unfortunate that I could not make it to the Netherlands, but I mean, we could still have fun online. So, my talk is going to be centered around how Rust Africa and I myself have been involved in the Rust ecosystem and in the educational system, and I see as being the best. So that's why I titled it Shaping Tomorrow's Software Engineer, Why Rust Belong in the Academy. I mean, the MC did a lot about me, but from the axis matter of mine, I'm a software engineer, a developer, and a system engineer. I'm the co-organizer of Rust Nigeria. I've worked lately in the African university system, taking Rust to the university system and trying to make sure that Rust stays there because I feel it belongs there. And aside from that, I've been working with the Rust educational team and the likes of Professor Brad, Ross 101 contributing there and also bringing in my idea due to the experience I have. This work has spanned across a lot of places and giving birth to what I call the Ross Africa Campus Store, which was a campus store that also brightened my view. Now, first of all, we need to understand what's the problem with the modern software education that we are having. The modern focus more on teaching people about framework, a lot of abstractions, and how to use a lot of people pass through the system, like the idea of how system work and how system are being built. I mean, it's not bad to use frameworks. It's not bad to use abstractions because it make your life easier. But it's nice to understand what is going on behind the wood. So what happens when the student graduates? When the students are graduating, they are graduating without having the knowledge of what memory is, what concurrency is, what is performance, how systems are being designed, reliability, what to trade off, why use this, and which is giving us a very, very bad system. Now, why does this matter at all? Why should I be thinking of why even understand the system when you are already building what is being usable by people? Now, software powers financial ecosystem lately with AI, transportation, and a lot of system. And most of this system, like the financial ecosystem, require a lot of security, performance. I mean, this is people's money we are talking about here. And the health ecosystem, people's lives. So you need to be careful. You need to understand every little speed really matter in the ecosystem, and then system and every other thing. So that is why you need to understand the system. Now, why Rust? Why are we talking about Rust? I mean, in the educational system, we already have a couple of nice languages there. We have C, we have Python. Why Rust? When we are asking about Rust, I mean, every Rustacean will know that Rust is memory safe, it has high performance, it's fearless in concurrency, and it has modern tooling. Now, this is one of the reasons why we want to put Rust there, because Rust have covers, to me, how I see and explain Rust to a beginner is more like Rust is this, has C, C++, and then Python code. So it's important to know that, and Rust help you understand what is happening in the system behind the hood and under the hood. So now this is why Rust is important to be pushed to the academy. Now, these are the things that when a student begin to learn Rust, these are the things that the student begin to understand which other language abstract. You could agree with me that in Rust, there's no way you are going to be learning Rust, there's no way you are going to be doing Rust, and then you are not understanding what ownership is. And by trying to understand ownership, you get to understand memory. By trying to understand thread, you get to understand how API are well designed, because Rust on its own is well designed. How a lot of error handling is works because Rust does not really allow you to do to let go of those, and then you get to understand how system is designed. So by just learning Rust on its own as a student, you get to have all these concepts which are very, very important, and then abstracted away by other programming language into your without having to separately have to learn it. Now, this is the experience I've had so far in Africa, teaching Rust to people, introducing it to their curriculum, and trying to get schools to adopt it. Now, for the first time, you always hear students say Rust is hard, it's difficult to learn, learning curve is steep, people try to understand. But later on, if after perception and giving them the learning and allowing them to learn for some time, you later get to hear them say, oh, I now understand how this system works. I mean, I've been writing this system, but I now know that this is the reason why this system is this. I now understand this is the reason why this work this way and this work this way. So this help a lot. This is something that this is a nice experience and a nice transformation power, because it's taking you from being a developer to an engineer who understand how things work a lot. Now, why was Rust really for in the academy? Why do you want to put Rust in the academy? Why am I really compelling to do this? Now, when you are learning Rust, you learn to understand how operating system work, compilers, embedded system, networking, blockchain infrastructure. In short, a lot of people are using Rust in AI now, XAI and the Rex, distributed system. So Rust is good and have a very good use case in all these areas. So learning Rust is like learning that one language that will save you the entire stress and also of doing a lot of things. And in the area where computing is very, very expensive, Rust is that one language where you will always want to go to, where you always want to use, because Rust is a bit, you can agree with me that a well-compiled Rust is cheap to compute or to upload to a server and manage. So this is one of the reasons why we are pushing Rust in the industry. We are seeing a lot of industry, a lot of Microsoft, Google, Amazon, the rest, even Linux now are using Rust. Now, the more Rust system engineers we have, the more Rust engineers who are thinking like, the more Rust developers who are thinking like engineers that we have in the ecosystem, that we are pushing into the ecosystem, is going to make hiring easy for this company. I mean, one of the compelling reason why I took Rust very, very serious and pushing it into the university system, because I'm a Python developer and I started learning Rust. I met some founders who had a product and their product was supposed to be built with Rust, but I told them this product is nice to be built. But the question that was thrown to me is, if we build this with Rust, how we will see other juniors or other developers who are writing Rust, because these developers are scarce. And I noticed that developers who are already in the system might not want to learn Rust, but going to people who are already learning and inculcating into their learning system would just be like a natural phenomenon. That's why I start going to the university, I start getting young people learning Rust and getting them want to be interested. Now, aside from the educational benefits, the industry also have to benefit a lot, because they in turn need this talent, and this talent is rarely made available from this process. Now, let me talk a little about some of the work we have been doing in West Africa. What have we been doing? We have been going to university, doing outreaches through university campus tour, and we have been doing meetups, we have been doing workshop. I mean, we did one of the largest Africa embedded workshop with Professor Brad. A lot of open source contributions. I'm an open source contributor. I've contributed to a lot of Rust project that I can't keep count. And then beginner education, in the sense that we provide beginner early curriculum that is well structured for easy learning and adaptability. We make sure we try to, I myself go around and teach this to people and try to make it very, very easy and very, very understandable. We have the mentorship program too, where we mentor young folks who are learning and who want to learn, who are having interest. And then Rust is something that you learn in community, because with learning it in community, you will enjoy this process at the end of the day. Now, the goal is to build a stronger system developers or engineers across Africa. Now, why Africa has the opportunity? Africa has like a lot of opportunity because we are still growing our engineering ecosystem in Africa and getting a lot of system developers. We help the technology industry, and then we help in advancement of technology in this thing, and also help in the global contribution to project that is going on. And we can see a lot of shift, a lot of people adopting us, and then we need this. Now, what challenges are we facing? What challenges is being faced as trying to inculcate system? I'm not just speaking as somebody who has been trying to do it in Africa. I mean, I have friends in Peru, I have friends other places, which I'm helping them trying to do this. I have professors from other universities. I've reached out to me. I've worked with Professor Brad, and then we are trying to do this in other universities across Europe. Now, one of the challenges we are facing that Ross has a steep learning curve. So we need to have a way to get university lecturers to learn this or try to go ourselves to teach this thing. Now, university moves slow. They don't want to change from, maybe they are doing their Java, they are doing their C, they don't want to change this thing. And then existing curriculum, they already have like a curriculum which they are using. They don't want to change this. They don't want to make it easier and make it changeable and all those things. So these are some of the issues we are facing. I mean, aside from, we are also facing some financial challenge moving from universities to universities and every other thing, which is fine, which is understandable. Now, what are the solutions? What are the solutions we have come up with, or what are the things we have done so far? For educators, this is what we have done. We start with a little workshop. We don't just go to this one and tell them, oh, we want to change our curriculum. We don't do that. We start with the workshop, get students to understand, learn Rust and how lovely language is, and then we make the student the advocate for change in their university, and then the change goes smoothly. And some of the things we do when we meet some of these lecturers, we explain to them, and rather trying to tell them that change your curriculum to Rust, we tell them now you can use Rust for, if you're having like some university have like introduction to computer science. Now you can use Rust as the language for introduction for computer science. You see, have the same curriculum, but what we are making you change is you have the programming language we're using. Maybe you're using Python, you're using C++ or C. You use Rust in this place. This now bring the student to liking the language, to searching more about the language and loving the language. So we introduce we use it to introduce system programming concept. Like for instance, if we are trying to introduce memory, we can use ownership method to introduce memory in system programming in universities to students. Now, by this doing, we try to infuse Rust into the system little by little by little, rather than just saying we want to change this. And then, I mean, this can be chaotic and this can bring issues. Now, for the students, what do? We allow the student to use the tool. We tell them how powerful the tool is. We allow them to build with it. We allow them to explore, and then we create them into group. What we try to do is, anytime we go to any university in Africa, we try to form a small learning unit in the school where they come together, they learn, they brainstorm, they have a community there that feel like a sense of ownership, and they start building things and they love the language. They now become the self-advocate for the language in their university, as I've said earlier on. So basically, these are the things we do, or these are the advice we pitch to people who are coming to want to inculcate this into the educational system. Now, what are my final thoughts? What is this sustainable? Is this nice? Yes, to me, these are my final thoughts. This is very, very nice, and these are something we should advocate for. Rust should be in the educational system. Rust should be where it should be, because then these are the people who are training system engineers. These are people who are training people who are thinking about the system. These are the people who are training people how the system works deeply. So now they should be using Rust, because Rust is the language for the future. Aside from that, we could know that personally, this is like my personal take, and Rust is the best language for AI, because AI is like where machine, now we are getting to the place where machine are writing the code and human are architecting the system. Now with Rust, which the compiler is already there to vet your system and know that this code is not having memory leaks, it's not having this, it's not having that. Combining it with AI, you have like your AI write your code, the Rust compiler do another check for you. Your AI write your code, the Rust compiler do another check for you, and then you are assured that if this code compile, you are less assured that your provided your logic is okay, your memory and every other thing concurrency and everything is well checked, provided because the Rust compiler is doing another work under the hood for you. That the compiler do not really care a lot about that, about all this process. You could end up shipping bug. So now, with even the future being machine writing code and human architecting system, which code into and all these things, Rust still become the best and still help you, because Rust compiler is meant to be your friend and check things for you. So now these are my final thought is allow for critical thinking, it allow for reliable software, it's create talent pool, a lot of talent pool to make Rust adoptable in the ecosystem, because a founder will want to see how good strong the talent system is if he or she want to hire or start using a certain framework, and this help in the Rust system. Now, thank you very much. This is the end of my talk. But will not be possible if I don't appreciate these following people. Scott Eno is one of the co-founder at Rust Africa. Daniela, who is one of our media person, and Enes, who is working with the foundation and have been very, very helpful in helping us structure some things and getting assistance we need from the foundation. Adosis, a German company who has been our sponsors in terms of travel, in terms of tour, and then Ross Job, which have been there for us with Alex at Ross Job have been very, very helpful in media publicity and getting us some things. And then Edu Ross, which has been one of the working and so pragmatics, and then a big shout out because the EduROS community is also starting the EduROS Refresh, which is a project we are working with Professor Brad to make sure that we bring a larger professors and people who are interested in EduROS and helping pushing EduROS into the system. You can check it out on the EduROS website and Zulip. And thank you very much. So that is the end of my talk. And if there's any question, I'm open to answer any question. Any difficulty we are facing, from experience, I could be able to advise you. I could point you out to some certain maybe documentation or things that is helpful to you. Thank you.
Thank you, Mordecai. We have time for maybe 1 or 2 questions. We have one here. We will pass the microphone.
Thank you, Mordecai, for your talk. I wonder to evangelize Rust into the curricula of universities, and if so, in which countries, which cities?
Okay, basically, I've done that in Nigeria. I've done that in the University of Benin in Nigeria. I've done that in the University of Uyo. We are doing that in Cameroon in a school called UDN in Cameroon. We are doing that, and then we are trying to also evangelize to Kenya and other places. But they are sub communities. Because the Rust Africa Initiative, there are sub communities in other universities which are still growing, and we are thinking of how to get it into the curriculum. Like I said, we start some communities and we allow the students to advocate. We have in South Africa, we have in Ghana, we have in Kenya, and then we have a lot everywhere, and they are still spamming up. So that is where we have gone to. And maybe it's one of the reasons why we are also having limitation is going to traveling and sponsorship and all those things have been a little less on advocating for this thing, because these things sometimes cost a lot of money and resources.
One more question.
Thanks for the talk, Mordecai. Logic speaking here. So what can the Rust community at large do to support the community in Africa to make it easier to recruit new members and to reduce keep people from becoming Rustaceans?
Okay, majorly, thank you for that question. One of the things that the Rust community could do, which is I've been working to shape it a lot, is providing some subtle curriculum that's the way the African community learn structure a new curriculum that make the African community to be able to learn easily. I mean, which is something I have already done, but I'm still trying to perfect it and put it out there for every other person. Aside from that, we need a lot of a bit of resources in terms of sponsorship, because as I said, these things cost a lot of traveling around the African community. You have to be in this university, you spend money, and then you have to set like a little community there in terms of having sometimes providing some form of maybe laptops or some things to these students, because they may necessarily not have these things. But then I think with that, with some good funding and then other things, everything is already put in place, because this has been a project ongoing for over 2 years. And as I said, appreciation to Professor Brad and the rest, because we have been able to ship a lot of things. Sometimes we do come together and have this synchronization of how's education working here. I mean, I have an article published on that which I could share with everyone, how African learn technology, and then we are trying to shape the ROS system into that and make it learnable by Africans. So far so good. We have a lot of developers in Africa. In ROS Nigeria alone, we have over 700 developers. In Cameroon, we have 300 ROS developers, and in Kenya, I think we have over 300 ROS developers. But we are still trying to get more people learning and getting more students learning. So thank you.
Any more questions? When will we see our first Rust Africa conference, Mordecai?
Thank you for that question. I mean, we are working on it. Very soon, let's say, we are in 2027, 2028. We'll be able to have like a Rust Africa conference where everybody will be there, and then we'll have a lot of fun. So thank you very much.
Thank you so much for the talk. Thank you.
Thank you.
Right, and before we move over to the lunch break, a couple announcements. If you have any allergies, go to HOP. That is the bar left at the front of... That was not correct. That was correct. Like the middle one, right?
Yes.
The new one is the middle one. Forget what I said. If you have allergies, go to the middle one. And we have 1 hour and 15 minutes until we see you back here for the next talks at 2 p.m. Thank you.
All right. Good afternoon, everyone. How was lunch? Cool. I'm supposed to mention some sponsors before we start. So first of all, there's OxidOS Automotive. I'm not sure if you have seen their stand, the booth downstairs. It's directly after the welcoming desk. OxidOS creates an operating system for cars. They work a lot in open source and they work on certifications for these operating systems to be used in cars. I met Orson last year at Eurorust. He's a nice guy, so be sure to check them out. And this is my YouTube moment. Thank you to ExpressVPN for sponsoring this conference. Seriously, I was waiting for this. I don't have any voucher though, so you can ask them downstairs if they have a 20% gift card. Also, thank you for sponsoring. Right, now to our next speaker. So I don't know if you've been in this track for the entire day, but it seems like, especially in this track, there's some bias towards JavaScript. So we had Algernon this morning with his sock puppets, having some very strong opinions about JavaScript. Then we had the Canva folks who, I think they even mentioned garbage together with JavaScript and not the collector. Who thought, what if you could have a web browser without JavaScript? So this is Nico. Nico works on web engines and UI frameworks in Rust. Nico works on Servo, maintains Blitz, which we are going to hear about. Taffy, a layout, and this is Lest.rs, a community guide to the Rust ecosystem, which I use daily. So thank you very much for doing this. And we are now going to hear about Blitz, a modular HTML and CSS rendering engine. Please give it up for Nico.
Hello, can people hear this? No, not yet. Ah, there we go. Okay, hi, I'm Nico. I'm here to Blitz, which is a web engine. I mean, it's just been explained, so I will start. So firstly, what modular web engine? So it's the core part of a web browser, Chrome, Firefox, and of course in Rust we have Servo, and we now also have Ladybird, if you guys haven't heard, which is pretty cool. Pointing out that a browser engine is kind of pretty similar to a GUI toolkit. They're different. They work slightly differently, but they also do basically all of the same things. They do layout, they do rendering, etc. And that may be worth bearing in mind as we go through this. This is by no means complete, but browser engines contain often some of these things. So networking, media decoding, and then a kind of a core of parsing HTML, a tree of nodes, a DOM representation, styling, so this is all of the CSS, layout and text, so making sure everything gets in the right place. Usually there's some kind of scripting, often JavaScript, but it doesn't have to be, as we may see soon. Accessibility tree, so that screen readers and such can access it. And you have some other bits around it, like you need to get input, you need to be able to interface with the system, windowing libraries, and you need to actually be able to paint things and render things. And traditionally, these are kind of monolithic, not completely. So if you use Chromium or something, I think you can customize the rendering backend, and you can certainly use Skia, which it uses its rendering backend without using Chromium. But a lot of this stuff, especially the stuff in the blue box here, it kind of comes as one, and you can't use a bit without the other bit. And I guess what I'm going to talk about today is, well, what if you could, and what might that look like, and how would you do it? There's some like different kinds of modularity that you may want to have. So the simplest is just being able to kind of turn bits off. If you don't want like video playback, for example, then you really don't want to include that because it's going to take up a huge amount of binary size. It's going to take up, maybe not RAM, depends. And there's a bunch of other things that you may not want. You may not want the JavaScript engine. You may not want to render content to screen at all if you're doing some kind of like automation thing or scraping websites. So yeah, generally for that in Rust, you would either want a feature flag or just have it in a separate crate, so you never have to pull it in the first place. The second thing you might want to do is like replace part of the engine. So say, for example, the rendering, you might not want to use the renderer that comes with the library. You might want to use a different one. You might want to use a videocoder or whatever it is. And in Rust, that's generally going to be like a trait. So rather than having a dependency on the concrete sublibrary, then you have it behind a trait, and you can have different implementations. And the third kind of thing is, well, suppose you do have an implementation in your browser engine. Well, what if you want to use that in something else? Again, generally you can't do that with the major browser engines, and this kind of includes even Servo, but not entirely. Some of them you can, but that's quite useful. So there's kind of three things. One, just turning things off. Two, kind of replacing functionality in the engine with something else external. And three, the other way around, where you take something that's in the engine and use that somewhere else. Now, that's what you could do, but why would you actually want to do that? So, okay, there's two whys in this why section. The second why is why would you want a modular browser engine? But the first why is just why did I even start this project in the first place? Just as a bit of background. So I work for a company called Dioxys Labs. They make this framework called Dioxys, which is basically, it's kind of like React or Solid.js, or pick your favorite JavaScript framework that renders in a browser to the DOM. And it is in Rust. This is some sample Dioxys code, and this is kind of what it produces. And you compile this to WebAssembly, and you can run it in the browser, and you can get a web app. We also have some different backends. So we have a web view, which uses the Rye crate from the Tari project, and that allows you to run it as a desktop app, essentially, although it's still a web view. You can also run it on the server. If you want to do like server-side rendering for your website, excuse me, need to breathe, then you can like pre-render it and you get SEO and stuff. And this project was, well, this is great and it's nice that we can do web stuff, but there's all these other cool frameworks in Rust that allow you to do like native GUI, GPU rendered. Emil's here, he does eGUI. There's Iced, there's Slint, there's GPUI. Oh, thank you. And at Dioxys, we were feeling a little bit left out. We kind of want to compete in this space as well. So that's what this kind of where this project is coming from. Can we take this exact same UI code and render that natively? Yeah, so project goals for Blitz. Number one, power the Dioxys native backend so we can compete with Electron and Flutter and React Native and Iced and Slint and eGUI, etc. Two, kind of once we'd started, we were like, well, this is kind of quite powerful. This can do quite a lot of things. So like maybe we could make this useful for some other things as well. So there's kind of a lot of things that are HTML adjacent, but not necessarily web pages. So like markdown content, often you want to render that, you know, embedded in something. You don't have full HTML, but you just have markdown. And then it's useful to have like a lightweight engine, right? Ebooks, so EPUB, is basically HTML. Doesn't tend to have much in the way of JavaScript, although I think it technically can. That actually requires pagination, which we don't support, but you know, we'll forget about that for now. Maybe eventually. JavaScript, lots of HTML. And things like rendering HTML to images or SVGs or PDFs, just so you can kind of get some output that you can export somewhere. So we want to support all of those. And then we were like, well, it's all very well supporting these alternative use cases, but we could just make a whole web browser, right? And there's some context around, you know, there's societal discussions around what it means to have an independent web. And we're thinking maybe we could help with that. So hypothesis that kind of Blitz makes that a healthy web doesn't just need more monolithic implementations of web browsers. This is kind of what Servo are doing, although Servo is semi-modular. And it's what Ladybird are doing. They're just building the whole thing, competing with Chrome and Firefox on their own terms. But this kind of hypothesis is, well, maybe it would be better if a browser was in pieces and you could share bits and not share other bits. And that might be more maintainable. Yeah, so some more whys. If your code places, more impact. It's just good engineering discipline to modularize things, right? We encapsulate things in structs and classes. This is not controversial. So why is it controversial when it comes to web browsers? Shouldn't be, in my opinion. And the other thing is, if you do get more users of your modules, then in theory, they might be able to help maintain those and provide more resources. Things like Skier and WGPU, they get resources from not just browser vendors, right? And this is just a quote, which I'm probably going to skip because it's long, but it's from the Chromium team about how they, I guess, with their massive code base, kind of decided that they needed to modularize things to just deal with it. A couple of why nots. I've had the whys. Okay, there's two bits to this section. Firstly, why am I not just using Servo? And secondly, why would you not want modularity? So why not Servo is like, Servo's pretty heavy. Minimum 70 megabytes, probably more like 100. 270 is a bit unfair because that includes all the media stuff, which you can exclude. But Blitz is more in the 5 to 25 range. It's a lot smaller. And yeah, Servo's monolithic, mostly. So you have to have the JavaScript engine. The whole DOM is built on the JavaScript engine. You also have to have web render. You can't do WGPU rendering, which everything else seems to be using. And it's kind of only really designed to be used as a whole. There are some modules, but for the most part. And the modules, they have something in common. They have two things in common. One, they were created when it was a Mozilla project. And two, well, yeah, most of them are actually in Firefox, and then they had to create the module. But they're not that many now. And yeah, I did kind of also try to do this as part of the Servo project to begin with. I contributed to Servo, but I wasn't getting a lot of, yeah, we want to do this. I was getting a lot more like, do we have to do this? So I figured it might be better to do a separate project. And I have some screenshots. This one is not very complementary to Servo. This is when I started 2 years ago. And there was a bit of a divide. So Blitz was really good at Flexbox and CSS Grid, which Google homepage uses, and Servo was not. But Servo was way better at the text stuff, and Blitz was not. So it may have made sense to kind of combine efforts, but that's not how it happened, and it's kind of difficult because there's different licenses. Blitz is MIT Apache 2 and Servo's MPL, and they mix if you have them in separate libraries, but they don't mix. You can't mix the actual code together, which is a bit annoying. Okay, and why not modularity? There are concerns around, these are the kind of concerns I've heard from other people when I've been trying to sell them modularity, which is kind of what I've been doing for the last 2 years. So, you know, can we still keep performance that's going to be competitive with Chrome or the like eventually, if we have these abstraction boundaries? Are we just going to hit a limit? Are there going to be like aspects of the web specifications that we can't, that we just can't implement if we have a boundary? I think there are concerns around code ownership. Like if core code to the web browser is sitting in some other repository somewhere that the browser project doesn't own, is that going to be a problem? And I think also just a concern around, we have limited resources, do we really want to focus them here? I guess I'm not really going to like directly address these in the talk, but I'm hoping that what I talk about, what I've done will be that much of a problem. So, how have I built a modular web browser? This is a section that didn't exist in the talk yesterday, and I realized really needed to be in here. And the answer is a lot of freaking traits. There's a more detailed answer coming. So this is our architecture. This is a complex one, so I'm going to take a while to go through this. But these crates beginning with Blitz and also the ones beginning with Dioxys are kind of the core Blitz itself, and everything else is a dependency. project. And it's also worth pointing out that Blitz DOM in the middle there with the big box, that's kind of the core of the engine. You can use that by itself, and it's quite useful by itself. And the other bits, so the Blitz DOM, it has a DOM tree, it has layout, and it has styling. And you still can't get any smaller than that with Blitz, even with our modular approach. Potentially at some point you could have just computed styles. Anyway. But what you have outside of that is you have any kind of rendering, the actual HTML parsing, you have the integration with Winit and the shell stuff, you have the networking. And then these numbers in the corner, these mysterious numbers, those are line of code counts, which I thought you might find interesting. Partly because, for example, BlitzNet has 420 lines of code. This is not a lot, but it rests on top of Hyper and Request, which have got like 30, 40,000 between them. And you can see a similar pattern across most of the modules here. We're depending on modules that are quite big, but our integration code is quite small. And I think that's kind of the aim. Yeah. And then a final thing to point out here is these words on the lines in between the modules. And those are kind of the names of the traits that allow the modules to interface with each other. And like, what are we actually doing to enable this modularity? I figured there's kind of a few strategies. They're mostly different traits, but perhaps it's worth being a bit more specific. So there are sync traits where one crate implements the trait and another crate pushes content into it. So the HTML5 parser is a good example of this, and the rendering is also a good example of this. There are pull traits where you have a data structure and you implement a trait that kind of allows some other crate to traverse that data structure. In Blitz, it's often a tree because the whole of web is trees of nodes. There's a delegate trait where you provide a trait that gets kind of called and that does something. Often those tend to be kind of going over a channel. And then there's kind of the more mundane things where you just have a third crate that calls the two crates and integrates them, or you just have one crate depend on another crate, but they don't depend on each other. In this section, I'm going to go through. I just want to say, I want to basically say that Stylo is amazing. You should know that it exists. It's part of the Servo project. It's used in Servo. It's used in Firefox. It's 100+ lines of 1,000 lines of code. And it is awesome, and it is like the poster child for a modular browser because so much of a browser is CSS. And it just does so much, which is listed. And then what we're trying to build in Blitz is layout. We have Taffy as the trait that we have Taffy. Traits are quite long. Stylo has a trait with 74 methods, and that's not the only trait you have to implement to make Stylo work. We have like 1,000 lines of code for Stylo, and there's 100,000 lines in the library. We have Parley. I'm going to skip through this quite quickly because there are some demos and I want to make sure I have them. Parley does text. So Taffy and Parley together do basically the whole of layout. There's a bit of integration code in Blitz DOM, but it's not crazy. It's worth calling out that Dioxys is modular. So it does state management and it pushes out like plain old data mutations that you can do Blitz. You can any render is cool. It's a 2D drawing library. If you're doing another GUI framework, you could consider using this. I don't have to. Generalize over 3 different forms of Velo and Skier. So we have 4 different rendering backends. You can implement your own. You can serialize the drawing commands. The CPU rendering backend is and such like, or if you want to render an image, you don't need a GPU at all. We have a custom widget API. So if you don't want to do HTML, if you're writing a native app and you want to do crazy stuff, then you can do this. So you can get access to, for example, attribute changes coming from the Dioxys code, and you can react to those. You can handle input events and such. I'm gonna. How much time have I got left? Okay. Drop the presentation now. Is that going to work? Yes. And show you some demos, and then we can come back to the rest afterwards if we have time. Okay, so this is Dioxys native. So Dioxys native is the integration of Blitz, the core engine, with the Dioxys reactivity framework. And this is what existed before I created Blitz. This is the version of Dioxys. You can see it's running in Firefox. This is a to-do MVC example. And then this down here is running the same code in exactly the same directory, compiling with different flags. So we're compiling with macOS and rendering native instead of web. And you can see that you get exactly the same app now with the native GPU renderer. What you could do is you can edit that app. So this is the CSS file for the app, and you get instant. Cool. And that CSS, you can also do this is the RSX, we call it. That will also hot reload, which I think is quite impressive. It can't do everything, but, you know, it's quite nice. Okay, was demo number 1. That's Dioxys native. This demo is something I've built with Blitz that does not use Dioxys. It's called RDME, like README, and it allows you to preview Markdown files. So this is the Blitz README MD. This is us rendering Markdown. It renders CSS styles, which I think is quite cool. And it also has hot reloading built in. So if I delete a paragraph over here, it deletes. I don't know what's happened to the logo there, but never mind. You can also do dark mode if you want to preview that. But I think this is actually genuinely useful because you get all of your tags and things which you don't normally get if you preview Markdown locally. And you can install this. Cargo install RDMD if you want to use it. Okay, so we've had Dioxys native. We've had something kind of rendering Markdown or HTML. Now the next thing is, well, what happens if you combine those? And then that's what you get is you get an actual browser. So this is the Blitz browser. This is the app. This, you know, all of the UI area. So you can browse the web. Hopefully, you have internet. So yeah, this is Wikipedia. It's always a bit of a gamble what's on the Wikipedia front page. I spend quite a lot of time on it these days, and sometimes the articles are different. I have no idea what this is. You can render the Rust Reddit, which is also a website that I frequent quite a lot. It's not perfect, but it's not bad. You get nice things like the CSS animations that will work. You can search, for example, for Dioxys. What else can you do? This is the website that I showed you before that did not work, and now it does, so that's good. You can go on something like Hacker News, and you can log in. In theory, we'll see how this goes. What we don't is password masking. But luckily, my password is longer than the box. That has not worked. Let's try that again one more time. No, okay, never mind. This did work for me earlier. Never mind. About 5 minutes. I have any other demos that I desperately want? These. What?
Google Maps.
That's not going to work. Every time I talk about Blitz, people ask me, does it compile to WebAssembly? And the answer is now yes. Although I think that other thing is taking the port that I need. So let's get rid of that and try that again. Here we go. So this is the 7 GUIs example that everyone seems to use when they get fed up of to-do MVC, rendered in WebAssembly, in Blitz. We don't really recommend you do this, but you can. Question now. And oh yeah, the other thing that's probably worth showing is the kind of custom widget stuff. So this is what you get if you do a custom widget. The spinning rectangle is kind of imperative Rust code that's drawing stuff. It follows, and it also can take in data from the kind of more declarative UI stuff. It's cool. Hopefully I haven't forgotten any important demos. Oh, yeah, you can embed it in Iced as well, or Bevy, or anything like that. So this is the top bit is Iced, and then this is just inside. I'm going to try and see if I can get through the rest of my slides. I don't have very many. Yeah, there have been some challenges. We did not solve all of the problems. And I'd say, like, getting code merged when there's only and provide review for yourself, and the other people are not working on the same thing can be a big problem. But I think that could be a slightly bigger team of, say, 2 or 3. And also, just getting crates to IO releases. Like, we depend on so many crates that if they don't all release frequently, they don't release at all. So there's a bunch of links here, which I'm not going to go through, but if you want to find them, I'm sure the slides will be posted somewhere at some point. And I want to just talk a little bit about the roadmap going forwards. So the things we want to do kind of in the immediate future, fix the layout. We don't implement position static or position fixed or absolute, or the absolute don't bubble. They don't bubble, which they should. There's a bunch of stuff with text. Vertical alignment doesn't work properly if you were paying attention on the you'd have seen is like, this doesn't look good. A bunch of rendering stuff, clipping, masking, filter effects. Really pushing on the custom elements so we can implement all the form controls, like select the password input that you saw, and like provide basically everything that the web shadow DOM and custom element APIs provide, but also ideally everything that the likes of Iced in the Rust ecosystem provide. There's a bunch of just events that we haven't implemented yet that we need to drag and drop, clipboard, etc. And we want to do DevTools, so you can't really inspect this currently, but you should be able to. So if I will do that now, they implement the Firefox DevTool protocol. You can open it in Firefox DevTools. Very cool. We should be able to do that, but we haven't done it yet. And there's, oh, this reminds me, there's a demo I have to show you. It is this one. So, you know we said we don't have any JavaScript? This is Blitz running with JavaScript. It's very experimental. It's been vibe coded and not by me. But you have click, you have request animation frame. It kind of works. But yes, what would we like to do eventually? Actually add JavaScript to this. I think it'd be cool. I've got 1 minute. It's my last slide, luckily. Do paginated layouts. You can do EPUB and PDF sensibly. I think that would be actually really useful. Loads of people do HTML to PDF, but you can't really do it currently. But you should be able to. First-party SVG, so we're not just using re-SVG. You can actually animate your SVGs and style your SVGs. System compositor integrations. You can get videos in there. You can do web views and things. Web views in your web view. Automation, so you can do like WebDriver, drive it with Playwright or something like that. Would be nice to have more layout modes, subgrid and the new ones, and yeah, rich text editing with content editable. These are all kind of like big things that I'd love to do at some point. If there are more people working on the project, hint, we have more funding at some point, or we've finished the other stuff. So yeah, if you want to get involved, come build a Dioxys native app, or just build something with Blitz or any of the other libraries. That's what they're there for. Come and help us build Blitz or Dioxys native. It's mostly been me. It would be amazing if there were more people. Or yeah, the browser app that you saw exists, and the Markdown preview app. If you want to just come and build an app that we've already started building, it'd be cool. And yeah, there's a bunch of links there. There's socials, project links, and then down the bottom, if you want to install the Markdown README app, then you can from there. And if you want to install the browser app, then you can, and you can do it now. You can do it on your phone. Oh, that's what I forgot to demo you, the Android version. Never mind. It works on your phone. Then you can go to the downloads link. It's there. Yeah, that's me.
Thank you. Thank you very much, Nico. This was amazing, incredible stuff that you've shown us. I'm pretty sure the audience has a couple of questions. So we have some time for questions. Please raise your hand if you have one. We have someone and following you around. Raise your hand. Yeah. in the front row.
Hi. So I something I didn't understand fully. So you said like it can be compiled in WebAssembly. That does that mean like you can run Blitz inside Firefox or something?
Yeah, I just showed you Blitz running inside Firefox.
Okay.
There's another question over there.
So RDME reminds me of MDCat, which I think recently disappeared. And when I last installed it, I saw it like pulling in web dependencies and curl. I was like, what is this application? So this is with Saner dependencies?
I mean, it still has about 300 dependencies. I think most Rust GUI stuff does, but it's certainly not pulling in like WebKit or anything like that, right? It is WGPU, it is Velo, it is Taffy, it does have Hyper and stuff like that, because you need to be able to fetch images and things like that if they're in there. And currently it does also, if you click a link, it will open it as a web page, because we were just using that for testing before, but it probably shouldn't be able to do that. I don't know. It's kind of like a product decision, not a technical one, right?
Cool. Let me see. So this is why I have those speaker notes too.
I have
cool, great, fantastic.
Awesome talk, really cool. I just want to see that I understand everything, and then I have a question. So when you do Deoxys native, everything is compiled to native, there's no WebAssembly or anything.
No WebAssembly if you're compiling to native.
That's awesome. Okay, so when you render this, can you explain like scrolling a huge page and everything like that? How is that handled?
So the layout and the style is incremental. That was very important. It was a release build on a fast MacBook, but it was pretty slow otherwise before that. The rendering itself is not currently incremental. It possibly should be at some point. So that is just rendering in real time, the actual rasterization bit.
So this is Velo GPU rendering just this viewport?
Yes, this is Velo hybrid, and it's rendering this viewport. And you scroll, it renders the new viewport.
First here, then here.
When I'm building Servo, I'm building something like 1,000 dependencies, and you just mentioned 300. What does Blitz do so differently?
It's partly just a reduced scope, so we don't have JavaScript, so there's no like Spider-Monkey dependency, or maybe 2 or 3 if you can count, but it's huge and it takes a long time to compile. Probably, you can compile 100 dependencies in that time. And there's things like WebGL, like XR stuff, video playback. The thing we've gone for with this is that you should be able to only compile in what you're actually using. So like the image crate, for example, has 20 different image codecs. We only enable 4 by default, which is like JPEG and BNG and GIF or whatever. If you want AVIF, if you want like some like weird codec, then you can. If you're deploying an app, then you might have control over which formats you need. Some of the bigger things are things like SVG. Like if you don't need SVG, don't compile it in. Or if you don't need networking, don't compile that in. I think the actual browser app is about 500 and something dependencies, but that does include things like a crate for like auto-suggesting the URL bar and SQLite for the persisting stuff. This is more application-specific stuff at that point.
Right, we have one more question over there.
Hi.
Hi.
So I was wondering what exactly makes text so difficult to render? Because you were having some... Sorry, it might be a bit of a silly question.
You should really ask the people who are sat directly behind you. But because this is where I get a lot of my knowledge from.
Sorry.
It's partly that there are so many different languages. And Latin text is one thing, but particularly like Arabic and Indic languages have a lot of like whirls and things, and you have to really actually render it correctly. And I think the other thing is just that like the actual glyphs are quite intricate. So if you want them to be legible, then you have to go to quite extreme lengths to like get really accurate. So you're kind of like optimizing that more than you otherwise. That makes sense.
Yeah, I guess that makes sense. Thank you.
I think we can have one more question. Let me see if there's still people having questions. Over there. Oh, okay. No, go over there. Sorry. I'm so sorry. You were first. Maybe we can too. Let me see.
Yeah, thanks for the great talk. You mentioned at the beginning that Dioxys currently uses Tauri for native compilation. It relies on the native web view, I think, of the OS.
Yeah.
So can we expect, or not expect, but how probable is it that future Dioxys native runs are gonna use Blitz?
The plan is basically to have them as separate backends. The web view is not going to go away. You can choose it if you want to, and there are probably legitimate reasons to do that. I mean, for example, say you want rich text editing. Well, there's no way to do that in Blitz currently. And there might be eventually, but in the short term, you know, in probably the next couple of years, they're not going to be, or at least not for the next 6 months, right? It will be opt-in, basically. If you compile with -- native, you'll get Blitz, and if you compile with -- web view or whatever the command ends up being, then you'll get the system web view.
All right, so there's one more question that we can do, and then we make ready for the room switch. It's so interesting, so this is why I allow so many questions. And personally, I have to say, this is a great project. So I've done web development for more than 25 years, and seeing this makes me really, really happy. So.
Yeah, hi, great talk. When you started building this,
Yes.
how did you decide on what to do with regards to like web standards and stuff, and like how you get like feature parity with Google and the other web browsers, and like what's the like plan to doing that?
So there are a couple of things to say about that. I'm just going to bring up the Blitz website because we have some kind of information. This is the download page, by the way, in case you're interested. We run the WPT tests, not the ones that require JavaScript, but there's the CSS subset, and we run about 15% of them, but that's still about 30,000 tests. And we currently score 42% or whatever that says, and you can see all the different subcategories. So that kind of gives us an idea of where we are, what we support, what we don't support. And we also have these statistics from Chrome that tell us down the side here what percentage of websites that Chrome visits, I guess a statistical sample, use that property. Unfortunately, it doesn't say which values of the property, so with display it's not that useful, but with other stuff it's way more useful. So we have this tracking, and we're kind of working our way down the list of which percentage is the highest.
Thank you very much. So Nico will be here for more questions. So if you have more questions, go meet him outside. And with that, let's have a big round of applause to Nico. We are switching gear. The next talk starts at 2:45. All right, welcome back to the Applied Rust track. Some more Applied Rust. I'm enjoying this track. So there's really great stories, and I'm very happy to announce our next speaker. Our next speaker is Michael Winkelmann. Michael is a computer graphics nerd since the age of 10. So 6 years ago, 7 years ago, something around that, yeah? And he worked previously at the Qt company as a software engineer and advisor. You might have seen him at different Rust conferences like Rust Lab, where he gave workshops about Slint. And now he's an independent software engineer. He's still trying to leave the C++ world, like we all do, I guess. And if you have ever seen those LOL CPP stickers lying around, ask him for more. And we're hearing about another passion project. So this is great. This is something that Michael is working on for a lot of time. We are going to hear about custom DSLs based on his story of micro CAD. So please give it up for Michael.
So, yeah, thanks a lot that I can be here, and it's amazing to see that many people in the audience. Yeah, so let's talk about domain-specific languages, and I want to talk about actually the Kiwa. It's a domain-specific language for trees, and these people living in Papua New Guinea, they like these pandanus trees, and it's very nutritious, and they have when they want to harvest the trees, they enter the holy forest, and it's holy for them. And when they start to enter this domain, they actually switch their entire vocabulary. So every word is, and because they don't want to awake the evil ghosts. That's the reason. And that's actually true. For instance, the word for scrotum in the language then suddenly means something hanging from a tree, which is totally funny. I totally see. But as a software engineer, we are using domain-specific languages on a daily basis, especially as Rustaceans. We're using we use Markdown for documentation, and I use Typst for presentations. So we use domain-specific languages, and that's really cool. And now we want to enter the holy domain of computer-aided design. So I designed my own language for computer-aided design using trees, not with trees, but we use trees. And yeah, so I thought, we're doing it like this. I guess everyone knows this gear, right? And I will live code this gear and in the language, and then just explain how it works, basically. And just to unload a bit that, because it can be a very high competitive load, I just mark down how basically the steps are how to design the gear. So the first thing is called the rim. That's basically the outer skirt of the gear. Then we have the teeth of the gear, of course, and we have the hubs, five hubs, and we have the holes. So basically, this is what you have to design. So, wait. Just let's go here. So this is the microcat. Oh, unsupported signal. What happened? Yeah. Yeah.
Okay. Oh, I stepped on a cable. I don't know if this was the reason.
Oh, that was,
okay.
Was me? Maybe? No.
Okay.
Yeah.
Oh, no. Oh, so the moment you move something, maybe you are using some graphic stuff that the projector does not understand?
Okay. I will try to change the screen resolution, maybe. Just...
Oh, they're good. That's good.
Yeah, wait until the moment we move something, so I'm trying to translate from the domain that I see into a language that you understand.
Yeah.
That the moment we highlight something on screen, the projector goes wiggly-woggly, and I jinxed it. I said today before we started, hey, we didn't have any display problems so far.
So this seems
okay,
to
yeah,
work
it looks better. Fantastic.
Okay, so I just changed the screen size.
No display problems.
Then we... Cool. Just have to rearrange the windows a bit. Wait. So yeah, let's code the... So this is the microcat viewer on the top left, and here is the source code. And yeah, let's start to live code the gears. So let's start from scratch. So first we have a radius with 50 millimeters, and we want to do a circle with the radius, right? So that's the circle. So we start with the rim, with the yellow thing. So we have another radius. Then the inner radius is something like 80% of the original radius, and then we can actually subtract this circle, and we have something that's already looking like a rim. That's cool. Now the second thing is the teeth, or the one gear tooth is actually a triangle, and we only want to use circles for designing. So how to triangulate a circle? So let's do it like this. So we first make a new circle, and then we move it like 10%, and then you will see here. I forgot this 10%. Yeah, here you see this tiny thing, and then we can actually also rotate it. So you are very familiar with the Rust builder pattern, I guess, so it won't confuse you too much. So here we can rotate it. Then we just do 3 points here. And you see we have something like a triangle, but we don't want to code this again, right? So we want to actually write it something like this. So yeah, so still works. And then we have this hull operator. So we have a triangle, cool. So let's give this thing a name. It's a tooth, right? Naming things is cool. Then we want to do the same thing again. So we want to have the entire polar array of the tooth. So we want the teeth actually. So we also want to repeat that. That's basically by the outer radius, and then we also need to do this rotation. We have that's what I learned in the preparation of this talk. The Rust gear has 32 teeth. So yeah. So let's do it like this, and we have teeth. Cool. So, and then you notice that we do the same operation here. We do this twice. We do, of course, we move in, we translate in X direction, and then we do this rotation thing. So we do a microcat for this. So we can do, let's call it polar array, it has a radius. We have a static type system, by the way. And then we can actually do this translate thingy here and write the same operation. And we can do n, same formula, and do it like this. And then we can actually remove this one here. And we just do that. And the radius. And here, same here. Teeth I said, so yeah. And that should do the same thing, so nothing has changed. The cool thing is, of course, I can also now change the number of teeth if I want to, if I just want to have 3. Yeah. So so let's give this stuff a name. So this is the teeth designed here, and the rim. We can now have binary operators, so we can union both the teeth and the rim. So the last thing we do is the third thing we do is the hub. The hub is very similar to the teeth, actually. So we have one hub is a circle, a bit larger, then a polar array, 5 with 5 corners, and same thing. So we have one hub, and the hubs is one hub in a polar array. We have 5 hubs, right? So 5, and we take the inner radius, and then we just hubs. So we have the hubs. Cool. Whew. And then the last thing we need to do is the holes. So the holes is just a circle of think like this. And we have the polar array of 5, right? So, and then we subtract the holes, so we have the gear. Cool. Almost. Thank you. So we want to modularize stuff, so we can actually write, it's called sketch in Microcad. So we have the sketch, and you can move basically everything that is here. We move in there, and then you can actually call this thing, right, to with 50 millimeters. So we can call it, and then we can apply an other operation to this. We can just say extrude this 5 millimeters, and then we have the gear. Yo, and then the last thing you can do, you can of course load other files. And let's go, because the R is actually missing, so we like to keep the Rust R here. So we have the Rust logo. Thanks. Okay, and the rest of my talk, I basically will just, that works. So actually this whole project got from OpenSCAD. Are there any OpenSCAD users here, by the way? Yes, a few, cool. So I was, or I'm still sometimes an OpenSCAD user myself, and I was doing lots of 3D printing back in the days. And I was always unhappy with the language somehow, and then I wanted to learn Rust. And I thought, you know, learning something, if you have a cool project to learn with, then it brings you forward, actually. And I decided, okay, let's just rewrite or try to rewrite OpenSCAD in Rust. And then it turned out, no, the OpenSCAD language, it's not that well. So let's redesign the whole language from scratch. We want everything. We want binary operators. We want assignments. We want this. We don't want any for loops. So we really want just give a clean slate and just design a new language in the end. So, oops. So when you compare, so this is, there's someone made the in the Rust artwork repository. There's actually an OpenSCAD version of the Rust logo, and then you see the old code here, and this is basically the new microcad code. So basically, this is the old to new. And you see, for instance, here you have for loops. In microcad, we don't need for loops because we have multiplicity. So basically, for it looked like this, and now it looks like this. So, and we have, oops. Why doesn't it go forward? Oops. Slides are slow. Yeah. Sorry, it's a bit. Okay, we have in OpenSCAD we have, for instance, no assignments, but in generally I think naming things is cool. So we have assignments in microcad, and we have no Boolean operators in microcad. So, and this is why where we noticed with these weird nested structs you always do when you OpenSCAD, that actually it's thinking the other way around. It's not normal PP thing. So as when I constructed the Rust gear, you notice, okay, you imagine a circle, you apply a translation to it, and then you rotate it, and then you do whatever you want. And OpenSCAD is always you rotate something, and then you translate, and then okay, it was a circle you actually wanted to deal with. So it doesn't make any sense. So that's why we basically introduced these binary operators, and then you actually see what you're actually working with and what you are combining. So that was basically the thing. And yeah, last year a friend of mine and I received the funding for the prototype from the prototype, and then we dropped it in the OpenSCAD community Reddit, and then it went a bit viral, and we got 4th place of Hacker News, and it got totally crazy. Then to do a bit expectation management, we are still in prototype mode because people started to basically to expect we replace basically the whole OpenSCAD and do you have this feature and that and that and that. So it's a very explorative project. So I just wanted to also explore languages in general. And then there was people, why do you develop a domain-specific language? Yeah, right. So, but the problem is that LLMs are fuzzy, and domain-specific languages they do not hallucinate. So you can actually you have a detailed output part of the microcad DSL design code. So we want to have the human code readable and writable, and we want declarative logic. So we don't want to describe what, but we want to describe what we want to do, but not how we want to do it. So this is basically want a parametric deterministic output. And of course, this project was driven by curiosity. You can learn something about building Rust itself, because you look at Rust language concept like the module system or something, and you see you investigate time how it's actually made, and then you see, okay, this thing is it's perfect, so we can just take it in our language and just rewrite basically the module system for MuCat. And of course, it's fun. So what does MuCat actually do? So essentially what we are doing is a string into a string, right? So we have a very string with very high dense information, and then we have a very long string which has really redundant information. And what basically the output is STL. It's a format 3D printing guys know. That's basically you can put it into a slicer and then you can actually print it or put it in a CNC milling machine or something. So this is basically the output. And yeah, of course, when we just want to convert a string to a string, we can just have the API. It's called fn microcat input string and then output string, right? And then we just ask Claude, implement everything for us, and then it's done. Yeah, no. So first, if we want to design a language, we need a grammar, right? So we need to fiddle also, and we want to explore the syntax a bit and things like that. And for that, we use Pest. Pest is really awesome. If you just, in the process of designing a language, you can basically have a parser generator, you have a DSL, in which you write grammar Pest files. And yeah, and so what you can actually do here, this is a snippet of the of the Pest grammar. Here, these little blocks here, these are actually also tests. So basically, we wrote a little tool in Build.rs that goes over the Pest grammar, and then it scans out these tests here, and then we can check if our grammar if every example we give here is actually working. And you just embed the grammar Pest file as a proc macro. And the problem is, but with Pest, when you start, and the whole thing starts to mature, then you see, okay, the error handling is not really good. You can only have one error. And the other thing is with some expressions, we had some shortcomings, so you can't do everything we couldn't do everything we want in Pest. But the cool thing is, we want a language, so we need to think about, okay, how to build a compiler. And if we want a compiler, we need trees, right? So we have the abstract syntax tree, we have the intermediate representation tree, we have the symbol tree, and then we have a model tree. So actually, then you need to basically build up compiler toolchain. So basically, you parse the microcat source file here, you parse it into the AST, you lower the abstract syntax tree into this intermediate representation, which means we basically simplify it. Then you try to resolve this tree into a symbol tree. The symbol tree basically contains these, like the microcat gear sketch and things, and the circle is a symbol. So we have to resolve the symbol tree. And actually, we're calling these symbols, and from that, we evaluate these symbols, and this will generate a big model tree, which is a bit like an HTML DOM, and this we can eventually render into an STL file. So this is basically, and I will just go in detail now to in each compiler phase. So the microcat lang parse. Create here. This is, by the way, just my slides are also online, and I just tried to, I was using Typst, and every time you see here this grayish box, that's always a crate. So you can click on it, and then you go to crates.io, and then you can see, okay, this is the crate. Like here, like Pest, Logos, Chomsky. So we replaced Pest eventually with Logos. That's a tokenizer, and then we were using Chomsky. That's a parser library for writing parsers. And it was really a good experience because we released, or did November, and then after Christmas, some random Dutch guy came and said, okay, I write a new parser for you, and not just drop the Pest thing away, and I will, let's discuss maybe what could we use for writing a parser. We had a discussion on Codeberg, and then I think he took 3 weekends for him, and he just wrote a almost production grade parser in Chomsky, and it was really awesome actually. And what was really helpful to using or developing this parser was Cargo Insta, which we use for snapshot testing, which is really useful because if you do changes in the grammar like that, then basically you notice that you can always trace and check basically the differences if you did something wrong, or if the result is as you intended. So this slide basically just every struct that is there in the language, so it's intentionally unreadable. Basically, it just shows if you want to develop a DSL, it's like solving 1,000 pieces puzzle. It's like really sticky work. And what crystallizes out, it's mostly for every DSL. You have something like statements on one hand, and then you have expressions on the other hand. So basically, a statement is something that's basically linearly called in the language, and then each statement can have expressions. And the cool thing in Rust, we can do this in enums. And yeah. And what you need, all of these syntax elements, they need source code referencing. So that means we need the range source code snippets, you need the line and the column, and you need the hash of the original source string. And this is mainly required for displaying errors and pointing to the original source code. So each compiler stage can produce errors as a specific source code reference. And then we need to display these errors. And this Miete or Miet library, which is really cool, but because it gives you these nice error messages and a reference. So this is basically anyhow on steroids, if you will. So next step. So we have the intermediate representation. So we passed the source tree. We have the abstract syntax tree now. Now we need to lower this syntax tree. And basically what we're doing, we're stripping off comments and white space and all this stuff. And we convert to base units. Basically, the base unit is always millimeter. And this is, I think, Rose gave the talk because I learned that every serious commercial cat engine uses fixed and floating points, so we should change it eventually. Yeah. And you can here in this phase, you can optimize even more in the future. So like solving binary operations and stuff like that, but we haven't done that yet. So next phase is the resolve phase. So we have this intermediate representation, and we want to get a symbol. So the symbol is like the Rust gear thingy here, and also this is basically on the right side. You see the symbol tree that gets out. So it has a root symbol that is from the document, and you have a standard symbol. It's actually a standard library. It's actually a symbol. And then you have an alias here, the circle, and this is our sketch Rust gear. So this is the resolved symbol tree. And you see libraries are symbols. So we have a microcat standard library that is implemented in microcat and is basically was loaded from file as a symbol. And this is a user-friendly web app for the built-in library, which is actually implemented in Rust. And this contains basically all the, let's say all the primitives and primitives you need. So also exposed as a symbol, and this basically directly calls a Rust function. So now, last step from the compiler toolchain, we want to convert a symbol, like the Rust gear, into an actual model so that we can render. And the model is a bit, if you have seen the talk before, it's a bit like a document object model, if you will. It's the closest analogy I could find. So if you see, this is the model output here, and when you look closer, you can see here, these are the actual models for drawing the circle. And you see here, okay, there's a translate operation, the built-in operation is eventually called, and here the circle, the workspace circle, and here another translate, and then here's the actual circle is drawn here, it's a built-in. And you will see that these are completely identical. So which means we can hash the models because we know from which parameters this was called, and each model will produce the same, or a unique hash depending on the parameters. And it means we can render the circles only once, right? So because we already just have to replicate it, which makes rendering re-rendering really fast in the viewer. And actually, because someone asked me yesterday, about compilation times, the main part of compilation time right now is happening on the render side, so we don't need to optimize the previous toolchain too much right now. We can really focus on optimizing the renderer. So, and the renderer is basically taking these models and it renders it into a triangle list. And there we use the CG mask rate for the vector geometry. We use the Rust geo trait for 2D Boolean operations and the manifold RS for 3D Boolean operations. So that's our plus manifold library. And it's the only C++ dependency in this project. But I'm really honest, so I don't want to, because the sticker is kind of provocative, no, but I don't want to criticize people in that, or because I wouldn't be standing here, we wouldn't be on the conference if there wasn't C++. So we have to, I think, give also the C++ audience a big bunch of respect that they brought us through here. And we are a progressive community, and I think we should drive forwards, but we should not. We should criticize the technology, and sometimes we know C++ is to be criticized sometimes. So this is what I just wanted to express with the low CPP sticker. So we have the architecture overview. I just have to be a bit tricky. So we have this 4 steps. The architecture, you see, okay, we have the same module, same trait, same context, same error is always the same. And we have a standard library with export, render functionality, and now we have a compiler. But now we need tooling. So we have the code formatter, then we have a markdown support, we have tests, so we can basically generate Rust unit tests from microcode code snippets, and we have a documentation generator. So regarding the formatter, we'll do it very quick. If you ever write your own code formatter, it's a task of hell. So I tested these approaches. So first, just you simply use the token and scan for scopes, and that didn't work at all, forget it. Then I tried pretty RS, that worked better, but then I had some very microcat specific corner cases that have not been covered. And then eventually I said, okay, let's go the hard way. Let's harden the syntax tree, have a complete syntax tree that also and the comments, which was actually eventually 3 weeks of full-time work. But yeah, it works good enough, but there's so much things to do. So it's a bottomless pit writing a code formatter. So be careful. Then we have MD book support, markdown support. So we have written a microcat language book, and this contains microcat snippets, and we want to actually eventually pass these snippets from the markdown and then eventually generate a build RS, generate a unit test from it. And that was during the project, because you can refactor stuff as you like, and you can just test all the code snippets again. If they are all working, then you know, okay, you didn't break anything. Then we have, just go quickly, we have these markdown code documentation. So this standard library here, and we want to pass the code snippets on the documentation from the standard library inside the doc comments, and then generate an MD book from it. And this is what you right now have. We could document more, I know, but basically this is the MD book that comes out from the source code right now. And then we have lots of applications that are using microcat. So we have the microcat command line interface. We have the viewer that uses Bevy as a 3D engine. We have a microcat. This is to inspect microcat files. This is using Slint as a UI toolkit. And we have language server, which is a bit of a mess right now, but okay. But we want to, what we actually want to is, because each of these applications is using microcat eventually, and we want a higher level API to abstract everything away, right? So we don't want to each time don't want to build up each time the compiler tool chain for each application. So we want kind of a driver. So this is what we have written, and then we are ending up here with this microcat input. No, forget. So this is our driver API, how it looks like now. So basically you have open a document, Rust gear, you import the traits, and then you basically can say, okay, document, compile, import. So this is the high-level API right now. Yeah, so the roadmap for 2026. So we want to, or I try to, it's quite ambitious, but I try to have a 0.0 draft for the language. So we have collected all the syntactic features we need. And this, if you want to join, your ideas are very welcome. We are in the cat industry. We want to do the toolchain refactor, compiler toolchain refactor, because we know it looked like when I showed these 4 trees, it looked like we just came to the drawing board and treat. Actually, it was a very iterative approach of doing it. So it just turned out in the last month, okay, it should be 4 trees. Before it could be 2 or 3 or 5. You know, but this is I refactored this a lot in the past months. But this basically has to be. It's not entirely completed, and I guess there will be lots of issues and pull requests. Then. Also, a very important topic is actually make it more easier usable. So we need to focus on the IDE plugins and the viewer interaction, and that's the LSP. And by the way, tomorrow I'm at the hackathon, so I will try to, if you are interested in language servers and IDE plugins some sort, I will hack on that tomorrow, the whole day. And also, we want to improve the dependency management for sharing UKIT libraries a bit. So because we want people to share their libraries and share their designs. More users are also welcome. So, and then I handed in a funding for application for an LNet that is basically want to implement a micro context pro server implementation. And more money is also welcome. Okay, thank you very much for your attention. Special thanks to these contributors. They did also an amazing job, just designing the language, making contribution, doing bug fixes, and so on. And I forget anyone here. Thanks to everyone who gave feedback, and thanks a lot for the Rust week that I could speak here. This is the project website. You find here's the code repository, and here's my slides. So thanks a lot.
Thank you so much, Micha. I wonder if the random Dutch guy that created the pull request is somewhere here in the audience. It would be so funny.
He is not here, but he will come tomorrow to the hackathon.
Oh, fantastic.
It's also the
Brilliant.
first time I meet him in person.
Cool.
We had
Brilliant.
just had 2 video calls right now, and he's very shy, I think, and he doesn't have a webcam, so I don't even know his face. So it was too funny.
But he will be not so random anymore.
Yeah,
starting
he's
tomorrow.
not random anymore. Icewind is not random anymore.
All right. So I think we have room for 1 or 2 questions. So over there, up here, and then Terz.
Thank you. You built a language that was so like Rust.
Yeah.
Did you consider writing it in a macro or otherwise extending the language?
Oh, yeah. The thing is,
don't boo macros.
I think what you don't want to. You want to have this instant feedback, with the viewer and everything, and that's. But it's good that you mention it because we looking at Rust concept and concepts in other language. We look also at Python, and OpenSCAD itself, and we always found how Rust did it was kind of the best. Like the module system, we have attributes. We have also certain keywords, that we don't need. Like we don't have traits or anything. Instead, we have operations, for instance. So but Rust was a very big piece of let's say inspiration. Yes.
I mean that's the natural way of life. First rewrite it in Rust and then put Rust everywhere.
Yeah.
All right, one more question. Ted had a question up there.
Thank you. Lovely talk. I loved all your tooling. I'm also in Rust, and the tooling turns out to be the hard part, or where a lot of the work eventually goes. One of the things I've been running into is that I have a tree sitter grammar for syntax highlighting, and then in comes somebody who's using Typst, or in comes somebody else who's using VS Code, or something else, and I keep having to write more syntax highlighting.
Mm-hmm.
Do you have any advice or strategies for dealing with that?
Not yet. Honestly, I have actually the same problem. I mean, what I did I put in the pest grammar in the LLM, and then it put out a good XML, which was at least good enough. I had to fix a few things, but it's already helping, But the thing is, it looks like there's also some abstraction layer needed, to do this, but it's apparently not there right now.
All right, thank you.
All right, I think we can afford one more question. Over there.
Thank you for a great talk and also a great demo. While giving the demo, I got stuck with something that I saw. Your arguments for the first operation that you extracted.
Mm-hmm.
It seemed the other way around when you used it, but still it worked. I was confused.
Okay. So actually, the argument do it differently in Rust. We do it by type, and we have some own rules to do that because we don't want to. It sees, okay, you mentioned, so the polar array function, it had an integer as argument and a length. And when you put in a length, then the order of argument doesn't matter because you see it sees it's a length and it what to get. So that's the idea.
Cool. All right. Thank you so much. Give it again up for Mika. And with that, we are switching gears pretty literally because after the short break, we meet at 3:30 with Harry van Haren and racing car simulation. See you at 3:30. All right, welcome back to the last talk until the big break. I'd like to welcome Harry van Haren. Harry likes racing cars, computers and programming, and he's a sim racing driver and not the Mario Kart kind of sim racing driver. Harry wrote open source Linux audio software 10 years ago, and you should totally ask him about it. And he's now writing telemetry software for racing car simulators, which we're going. So please give it up for Harry.
All right, thank you very much. Hello, everyone. So Harry van Haren is my name. As I mentioned, I'm going to be talking a little bit about racing in Rust and building telemetry tools for racing simulators. Very quick intro. Most people probably know what a racing simulator is, but fundamentally it means you're playing a computer game, mostly PC-based if you want to take simulation very seriously. This is a picture of the rig I am lucky enough to have at home. We're talking triple screens. You have a PC, you have a little steering wheel, some pedals, a bucket seat, right? One of these ones that kind of wraps around you. You push quite hard against the back of the seat, so you need a good chair. Other things that are important for a good experience when you're playing this game is having some hardware. So you can see the little steering wheel and the big black box behind it. That's a wheel base. It's a big electronic engine, and it actually puts quite a bit of force on your hands when you're holding the steering wheel. So when you drive a car on your way home, you'll notice that, the car kind of goes back to the center a little. That, like, your full pressure of your arm is trying to twist that steering wheel, and the car wants to go straight on, and you need to make it turn the corner. And that actually helps you understand how the car is feeling. So it's really important for doing racing experience, you get that physical feedback into your arms from what the car in the digital world is actually doing. Grow nerves into the steering wheel to kind of understand how the car is feeling. It's kind of an interesting thing. But that's kind of how you interact. You need a good brake pedal because going fast is easy. You press the right one, but slowing down is much harder. You have to press the brake pedal really hard. Ask me about details later. The techie bits for now. So what is it we're actually working to? A picture of, okay, so what do you play? What are we trying to build? And then how the Rust bits fit in overall. I'm working the recorder developer, and I'll tell exactly what that is in a second, for a project called popometer.io. This is set up by someone, Nils Naujoks, in the sim racing community. He's known. He's running the Popometer project. What it does is it allows you to compare your driving style and your abilities in the sim against professional drivers. So these are folks who do real life GT3 racing and who also drive sim racing for practice purposes. They record their laps and they can see exactly what inputs and things they're doing. And you can now compare your driving style against. The good news is you can learn a lot. The bad news is you'll realize how bad you are, or at least in my case. So the really, really nice thing is you have the same configuration, the same car, the same setup, and that basically means suspension, tire pressures, for mechanics. Same track, same air temperature, same track temperature, things like that. And I mentioned the recording as you drive, then either on kind of a web view, so this is a website screenshot, and you can see where your driving was different, where you put the car, where the placement of your car was different to the pro driver. So how Rust where, if you want to know. This is me. I'm ready for a sim racing session. I have my safety gear on. We like safety, I hear, in the Rust community. I have my steering wheel and my pedals, and I've loaded my favorite game, Assetto Corsa Competizione. It has a lot of GT3 cars, which happens to be my favorite thing. So we're playing the game. How do we get data out of this game, right? The game itself has a shared memory output mode. The geometry that the game internally is being exported. You don't need to go and hack into the game's memory or anything. It is. It also gives you a C header file, which basically describes the ABI or application binary layout of that data. So we do a little bind genning to convert one to the other, and then we're basically golden to go. So what does the recorder do, or rather Rust where? The orange arrows kind of indicate what was built in Rust. So we read from the shared memory segment and we can pull out the materials. So things like tire pressures, engine RPM, gear, steering, throttle, brake, all of those things are available there, including a lot more detail that you think might not be so interesting, like tire temperature. But those things are extremely interesting if you're really trying to be a professional racing driver. So what is the actual UI built in? That's NWG UI toolkit based on Windows. It basically shims into the Windows Win32. Quite nice to work with. So it's a little user interface just to kind of make sure that locally the recorder app is running and it's doing what it thinks it should be. It has an SHM, shared memory, frame gap, so you can kind of see, are you accurately memory from the game, or are missing data at times because your computer's not keeping up. Those are kind of important things. And then whatever we scrape from that shared memory structure, we upload to the web servers of popometer.io, and that's where the actual process and the web view is then. So that's roughly how Rust is used. So let's talk about building it in Rust, right? Bindgen, the header file, I talked about that. SHM map view of file. A little bit of unsafe there, right? You have to take a Windows RS crate handle thingy, which version of the Windows crate you're on. That's improving quite a lot recently, actually. So yeah, I'm not even sure that strictly requires unsafe anymore. You read that data, so you essentially cast Bindgen Rust struct. You do some not pretty, but it does work. Because it's a shared memory handle, you kind of know it's going to be around forever until you close it yourself. So there's a little bit. If I was to say what's the ugliest Rust code there, just data out, so you kind of forget about it. And then you upload it, minrec, Russell's RustLS, and a few other things to enable that connection and do the upload. You need a few little tricks in there somewhere to make sure you don't swamp connections and things. I'll talk about that later. But then you do a commit, 10 files changed, 1,000 lines, and it just works. No seg faults, and the data arrived where it was intended. So that was a real experience that development before and things. But I wouldn't have expected this to work first time. So that was a really good experience. Then maintaining it. So obviously software is write once and maintain forever. So 16 releases in about 3 years or so. We added some features, UI, UX improvements. So the little UI got a few more counters, some few extra buttons. We done some testing, so you want to make sure, follow the little orange arrow, the lap time, so that's your overall time going around some circuit or a track, needs to be exactly the same as what the game perceives it to be in the website. Like, you want to make sure your timings are actually correct, things like that. It's kind of the aim of the game, right? To have the lap time be the definitive measure of better is lower lap time, as in faster around the track. We added a lot more games, so Assetto Corsa Competizione, the one mentioned earlier, Automobilista 2, iRacing, very popular platform, LMU, Le Mans Ultimate, so relatively newer game focusing on the Le Mans racing series, R-Factor 2, somewhat older game, but very interactive, and you can write plugins into that and do all sorts of crazy things. That's really nice that you can do lots of crazy things. It also has a second. Fundamentally, refactoring is always kind of a key if you're building a little application and it's refactor it, you add. Now, having one thread do network upload, reading shared telemetry, and you run work. As soon as you hit a network upload, you're going to stall for, I don't know, a couple of 100 milliseconds most likely before you've uploaded a block of data, which means you've now missed a whole bunch of telemetry that the game does because it basically overwrites its previous version of the data. So you split it into a data main thread and you say, hey, this is all good. And then you realize your user interface thread is now non-responsive because you're doing network thread, so you split it 3 ways. All of these things perfectly fine. So you use MPSC channels or some kind of way of distributing messages across the application. You have 3 threads running in parallel, 0 issues. Right? Most have probably done something similar, and that was really nice. But no bugs at all. You might say, hey Harry, no one's actually using your software. That's also not quite true. So there's 4.8 million laps as of recently driven with this telemetry thing. If you do the maths, the shortest lap time I think anyone's ever done in that is about 1:20. You can multiply that out by at the least 1:20 times by 4.8 million. It's years of drive time. So that's pretty cool. It's also about 20 terabytes of data uploaded, and that is so we can entire telemetry block before we upload it. Of course, you want to minimize network bandwidth. Depending on the game, the compression ratio changes a lot, so it's kind of hard to figure how captured if you want or whatever. So Rust works, nothing to improve. There are some things we can do better. So far it's mostly successful. Picture, you can see there's some space left over there. Features. And let's add some cool features like a live telemetry overlay over your application. So we want to be driving and we want to see, for example, where are we on track? Mostly you know if the next turn is left or right. I hope you do 200 and something kilometers an hour. But it is nice to see the overlay of the foot pedals in particular, so the accelerator and the brake. because you can learn a lot from a pro driver, what they're doing with the brake in particular, but accelerator and brake, and what the steering wheel input is at that point in time as well, where the car is positioned. So we want to overload those things live as you're driving. We want to have as low latency as possible, up-to-date information overlaid on the screen, so in front of the game, with transparency so that you can still see the game in the background. So what that looks like is the bottom right. So that's kind of what's being generated, the telemetry, like the Popometer recorder application, and then we're overlaying it on the game on top, right? So you can kind of see how that works. This is a more full screen screenshot, so you can kind of visualize that in the text. The bar up top here with the little start finish line shows accelerator, and then the faded green and the faded red is the professional's lap behind it, and those are in sync. So what you end up with is a nice overview of what's happening from what you were doing, and that's like in the past, so you can see kind of that starts in the middle and goes to the left. But on the right, you can see what the pro is about to do next. So you can actually anticipate, okay, I should brake it, hit the brake pedal as hard as you can. Learn very, very quickly from this telemetry being displayed live over the game as you're driving, and that's kind of the feature that we're chasing here. So how did we build that? Well, with WGPU, very cool crate. It was mentioned earlier on in the Blitz web browser talk as well, and in lots of other places in the conference. So yeah, a very cool project. The overlay is written in Rust. It uses WGPU for GPU access. On the Vulkan backend is how I developed it. This all worked pretty well on my hardware. There are hardware caveats here. It turns out different GPU vendors have different, particularly on the transparent overlay thing, there's just differences and nuances in what shaders work well and how that alpha pre-multiply and things like that actually have to be implemented. So this stuff is not easy. Particularly, it's not easy for one developer who has access to one machine to develop something that works across the. So those are things, not criticism of WGPU at all, but more a criticism of the overall, or a statement of fact, I guess, of where the industry is as different GPU hardware vendors and things are. Highly recommend WGPU. I can't point at how I would do better in scenarios. It's just the statement of fact that some of the ecosystem is not super friendly. It also turns out that GPU shader code can actually segfault. So not something that I've had recently in the Rust land is segfaults and generally bad things. It's actually quite easy to do that. So that's kind of unfortunate. What that looks like, vertex info, so that's float 32s usually, around this track. So let's take this example. We have a long track. That's this particular track. It's the 24 hours layout of Nürburgring. And it has a lot of vertex data all the way around, and we want to plot that in that driver or in that shader. So you upload all of that, and because you want to save on data size and things to upload, because you're running a fully fledged game in the background, right? You want this overlay to be as lightweight as possible. You use a lot of tricks around indexing between different arrays to avoid data duplication. And if those indexes go out of sync, you just basically access something outside of an array bounds, and then the code blows up. Or rather, your GPU says, hey, I can't do that. GPU or WGPU does give us good error messages and things like, hey, you accessed out of bounds on this particular array, blah, blah, blah. Right? This is not the norm system to do runtime debug and things like that at that level. So there are some improvements possible there, and Vulkan is doing a lot of validation of some of the input commands you do. So there's active work in that area, but still you can easily segfault in your GPU shader code. I have bonus content because I was 5, of which I probably still have 3. So let's talk about ABIs a bit more, because we all love a good ABI story, right? I mentioned more that it has a plugin interface. That is a C++ plugin API, not C, C++. That matters about backwards compatibility and things, and there are about 7 versions, if not more by now, of that plugin API. So it's a bit fun to play with that. Then you've got your code now hosted in the game itself, but you still need to extract that out to the Popometer recorder, right? So you invent your own shared memory API to move that data across. A little bit of a kludge or not clean architecture perhaps, but it does work. Experience with shared memory ABIs and things like that, we built in a lot of ABI mismatch checks that if I update the background shared object that gets loaded into the game, don't match the same ABI version, throw up a big request that part of the thing, because that's installed in a user arbitrary location. I can't even install my shared object into the game because I don't know where the game's installed. So it's tricky. Some of this stuff is pretty, human intervention required at the start to install these things. But it does work, and we can now present a nice user, nice error message. Error messages are never nice, but this is a nice error message, and open a web page to instructions on how to fix that for the user. So that's kind of good. I mentioned about the vertex indexing shortly, but if you want to look more at the details of what that looks like, we have the WGS. So this is actual, like, Wixel, I guess people call it. So that will be compiled by the GPU driver and run on the GPU cores itself. Then we have the ABI compatible Rust code. So this is like the same binary layout, normal, that enforce the ABI layout, and then a whole bunch of things to figure out how to send commands with that exact ABI or upload that into the GPU. Because the ABIs match, you can now use this struct, fill it in, and then send it to the GPU side, and there that will have the same meaning. But this is it's kind of like bind gen to a C header file, I guess. I don't know, are there better ways to do it? I done this manually and just kind of error checked it and toyed around with it. That worked. The buffer, bind buffer layout and things, that's part of the WGPU crate, and how you GPU, those kind of things. That all works pretty well. I couldn't do better. What they're very nice is names. Everything, like you get a tag or a name for each command and each descriptor, and that's an option string, I think. Option maybe. That you can that because you name all of your commands and all your descriptors, if something goes wrong, it says, in this stage, upload data to GPU. You had an operation called globals where you upload the resolution. This resolution made no sense. And then you're like, okay, I'll go debug that bit then. And that's really, really helpful, because otherwise it blows up and you just get, didn't work. And then you don't know where to start searching. So in terms of, being able to kind of identify where the hotspots are, so overall, look, this has been a lot of fun to work on. I don't have a live demo. I couldn't bring SimRig. Maybe next year, if someone's kind enough to bring a SimRig, we can play a few games. But if anyone's interested, look, Popometer is the project. I'd be happy to hear from users' experience. If there's sim racing folks in the audience, definitely ask some tough questions. To summarize, the production of building this with Rust has been super positive. The ecosystem has been good. There's actually the iRacing game has some telemetry crates and things already. So we're sample code and things around things. This is real world deployed code. It's actually probably like the most, and there was kind of no oopsie bugs in the refactors and things. That was really kind of eye-opening in the production sense. Like, okay, you can hack on something at home and it works on my machine, but this works on many users' machines without issues. So that's really impressive. So with that, look, thanks for listening. Thanks for everyone in the Rust community for building really cool software, and happy to take questions.
Thank you, Harry. All right, we have some room for questions. So let me see if I can spot some hands. Or please shout. Over there. First hand that is spotted. Fourth row. Flight simulators.
Flight simulators. Yes, I don't have one. But do you have a game or a thing or telemetry? Is there a similar kind of niche or things in that domain? Cool. Okay, let's talk after this. It seems like you have a lot of cool questions and ideas for me. So yeah, sure, let's talk. Thanks.
Next question is over there. No, sorry. We have a microphone over there. I come to you later. Still all right? Shoot.
Yeah, sure. Just regarding the UI, when you have the comparison, like when the professional drivers brake and accelerate, did you experiment with maybe using audio for this? Because it's like less distracting. You can still watch the road, and then maybe there's audio cues to follow the professional driver.
Beep, 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 and start braking, for example?
For instance. Yeah.
Cool. There are other projects in the sim racing community who use audio cues to indicate certain driving aspects. One of the things that you care about a lot as a driver is a slip angle. So it's like the angle that the tires are scrubbing that they're not facing. So if you're driving in a straight line, your slip angle is 0. But if you have 90 degrees on the wheels, you understand, then your slip angle is 90 degrees. So your slip angle is something that's really important to try and optimize, because tires have more grip at certain slip angles. And some of these projects use higher and lower pitched beeping noises, so beep, 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 based on how good your slip angle is. So you're hearing this kind of beep, beep, beep noise, and you can try and tune to that. The danger is if you ever go to real car racing, you don't have that anymore. So you're kind of learning non-realistic driving techniques, I guess. So there definitely are things around learning a track. So understanding for the first time where to brake, it can be very useful. But usually this kind of overlay I'd use for maybe 4 or 5 laps to understand exactly what, and then go back in future if I can't out, you'd go back and refer in detail to things. This is only the live overlay. I didn't actually pull screenshots of the website, but there you can zoom into one corner and there's like markers on the apex for the apex speed and the apex location and a huge amount more detail on driving style and things. So interesting concept to use different types of cues. I like it. It does exist a bit in the industry. Thanks, good question.
Right, and you got the microphone? Yeah. Cool, then shoot.
How long has it taken on average to add a new racing game to the API? Say, for example, I want to add BeamNG Drive to it. Like, how long would that be expected to take?
Great question. Not long at all. The more difficult part is actually kind of plumbing it into the wider applications and things to send. Around kind of one thread does the SHM, the shared memory kind of reads and things, and then sends messages to the UI into the network thread. So there is kind of touch points there. I should state, so unfortunately you won't be able to add BeamNG or other games yourself. That said, you can build very similar things with BeamNG, I'm sure, and pull that data out and work with it that way. So it shouldn't be a large lift. In theory, you could imagine you build a trait provider or something. The common functionality you would have is these 2 ring buffers, and kind of the fact that message out different, as I mentioned, checked as plugins where you invent your own SHM API. Some have a dedicated SHM API. I think iRacing has like kind of a binary hash map structure over. Very interesting, and they have their own reasons for doing that. It's not a bad design decision, it's an interesting design decision. So it just depends on your use case and things. So there's very little commonality across the games, apart from the very fundamental read data. And yeah, I didn't build a trait for that reason. I just have a bunch of logic to spawn the right threads and game function.
All right, I'm sure there are more questions. Harry will be here for the break, so if you have more questions, you can ask him. I have one, if I'm allowed to. Did you ever experience... That sounds enough. Thank you very much. All right, please give it up for Harry.
Thank you. Thanks, everyone.
We're entering a break. There are snacks and refreshments. There's fun. Talks continue at 4:20 for the last block of the day. Thank you very much.
Greetings, everyone. Welcome back. Before we start with our next talk, I would like to take the opportunity to thank our sponsors. We have 3 more sponsors to announce right now. These are the Unconf partners, which are Microsoft, Vectorware, and Ferro Systems. Big applause for them. Now, this is a very packed room, and rightfully so, because a lot of people were looking forward to this specific talk. I personally am. These slides, the ones that I hold in my hand, the cards, are made with the system that Lawrence will talk about now. It's an alternative to LaTeX. It's a system written in Rust. I won't say much else about it other than introducing our speaker, Lawrence Metier, who is the primary maintainer and CTO at Typst. And he started Typst with a friend during a CS bachelor's degree. And he wrote his master's thesis on it too, and then founded the Typst company. Big round of applause for Lawrence Metier.
Thanks for the intro. Am I live? Yeah. Okay. Hi, everyone. So I have for you today a talk about my kind of favorite topic. And I definitely did want to show off some of the cool stuff that we built. But I figured it would also be interesting to give a bit of a bird's eye view on how you can design and implement a language with both things working together for a common goal. But before we get into that, I would like to bring everybody onto the same page about Typst. So it is a markup-based typesetting system that compiles Typst markup, so domain-specific language, into PDFs, image files, or HTML documents. And when starting Typst, we had a few design goals in mind. So we wanted it to be easy to learn, we wanted it to be pleasant to use, we wanted it to be just an overall friendly system. An example would be that we are putting effort into providing clear diagnostics, which is something I've really come to appreciate when working with Rust. But perhaps the most central goal of all with Typst was to realize live preview, because I've been working with LaTeX in my bachelor's, and I just couldn't see that spinning compile button anymore. I want to see right away what I'm doing, and this should be possible in the year 2026 with the hardware they gave us, so that's what this talk is about. What you can do if you co-design your language and your implementation to support performance. And first, maybe a brief overview over what we'll need to support with this compiler, meaning what needs to be fast for incremental compilation to be real. So Typst has its own markup for math, code, and just prose. And there's some examples here on screen. It's a bit like Markdown, but like the details don't really matter. It's just that you have a rough idea of what we're working with. Typst also has its own styling system, which mostly comprises these 2 primitives, set rules and show rules. And these can be used to style the document independently from its content. For example, we can set the heading numbering, and then this is applied to the whole document, and then have this number 1 on my heading. But I could also say that all my strong emphasis elements, which are these like words surrounded with asterisks, should be red, and then it will do that. And then, of course, the compiler needs to resolve these style rules efficiently, incrementally. Then Typst has a scripting layer, basically a full scripting language built into it. It has functions and modules. You can write a Fibonacci function, but you can really write anything you want. So the compiler needs to process function calls, handle modules, and all that stuff. And last but not least for this talk is the introspection system, with which the document can observe itself. As an example here on slide, you can see that we can ask Typst, where is the only heading in this case in the document? Give me literally its position on the page. And then it will tell you it's page 1, these coordinates. So we have a couple of things, a suite of features that we'll need to support. How do we approach that? Of course, we can always write code carefully with performance in mind. And as Rust developers, we've got to chase down those allocations and avoid those logs. While we do care about that, it's not the topic of the talk today. Instead, we want to throw RAM at the problem. Sorry, wrong picture. I think I'm the 5th person to make that joke, sorry. we want to, for remember the problem, to remember intermediate compilation results. Because when you're editing your document, you're typically doing that in a session. So there's small incremental edits to the document, and you want to reuse as much of the work between these edits as possible. So that's the first thing I want to talk about today, how Typst remembers stuff across these edits. And we'll start with layout, because it's actually one of the things that's easiest to remember. So take a look at this example. We have 2 paragraphs and an image. Now, if I type in the second paragraph, the first one, it's not going to change, like how? And this fact reflects in the code. Because if you have this layout function, it takes a paragraph, it takes a width, and it builds what we call a frame, which is basically just a rectangle with a fixed width, fixed height, and stuff like elements at fixed positions. It's fully layouted. If you have that function, then you can see, given the same inputs, like it will produce the same outputs. It doesn't make sense to do anything else. It's deterministic. And it also doesn't make sense for it to have side effects. There's no mutable reference parameter. There's no global shenanigans or anything. The function is pure, and it's very easy to cache. So you just hash these inputs. We use zip hash, which I believe is also what Rusty uses, unless they've changed. And then we store the result in a hash map. And that's it. Like, we have this attribute in Typst from this crate called commemo, which we've built and use for incremental compilation. But it's really, at this point, very simple. And the results aren't too bad. Like, this brings you quite far already in terms of speeding up specifically the Typst compiler, because layout is fairly expensive. It's very easy, but easy solutions are often the best solutions. Yet, as you might have guessed, it's also not the full story here, because we have this whole scripting system, right? So we have modules. You can use them to split content with include, and you can use it to organize your scripting into modules with import. And we don't want to reevaluate all modules every time a single one changes, obviously. So we want to memorize module evaluation. Now, if we go back to the code, imagine an eval function. It takes a source file and it produces a module. Let's see how that works out on an example. We have a very simple example, just a main file that includes a chapter file, and then we have a chapter file with some textual content. Like, how is that eval function supposed to work? Like, if we're evaluating the main file, we got to somehow read the contents of the chapter file, because we only then know that it's importing that file or including. So, and that's all nice, but it doesn't really work well with memorization, because the memorization system relies on all the information that can somehow affect the flow of computation and the output to go into the hash, because otherwise it will just have invalid cache hits. If we just hash the path buff here, then it will not pick up changes to the files. So hashing just the path is not enough. We have to find some other approach. So we could make this file system eagerly contain all the files. And now this works, but incremental compilation has just gotten ineffective, because now the hash contains the sources of all the files, and if any file changes, the hash of the fs changes, and then all the eval calls will be invalidated. So the problem we have is that we have some input, some large input of which only a small part is observed. But we cannot say statically which part it is. So we somehow do something at runtime to track this. And in commemo, this is realized with this tracked wrapper type. We wrap the fs in this track type, and we add this commemo.track attribute. And what happens now is that every time we call this fs.load function somewhere in the flow of computation of eval, we literally remember the arguments it was called with. So in our example, we have these 2 load calls, and we remember a hash of the return value load gave us. And this is what we call a constraint. And then when we're done evaluating a module, we store these constraints alongside the output of eval, and also with the key hash. And the key hash is just what we saw before, basically a hash of all the non-tracked arguments. We put that into the cache, and then the next time eval is called, we can hash the non-tracked arguments, look for the key hash, find the different entries. There can be multiple entries with different constraints, and we try to find an entry where all the constraints match. Now, naively implemented, as was obviously originally done, because that's always what you do first, this has quadratic complexity in some cases. We figured something out, now it's a tree, and it works. And this is really basically all that's happening to make the core incremental system in types work. So this is where the co-income memo comes from. It stands for constraint memoization. We have these constraints. And with this, the stages is set, so to speak. We have plain memoization and we have constraint memoization, the two incrementality primitives in the Typst compiler. We can cache layout, we can cache modules in a fine-grained manner. But there's still some more I want to talk about. And now we're getting slowly into the design part, because what about functions, like user functions? How do we cache those? Because functions in types, or the whole scripting system at large, permeates the styling and the layout. Layout can trigger styling can trigger functions can trigger layout. So everything is interconnected and everything must be cacheable, including functions. So let's say we write a function like this that increments a counter. Now we could somehow try and replay the side effects of that function if we cache it. But we could also try to take the plunge and see what happens if we just force user-defined functions to be pure. The design approach just being, let's just play this out and see what happens. Now, there is the valid concern of, do we immediately become Haskell? And if yes, how is it going with that whole easy-to-learn thing that I spoke about earlier? I would argue we actually don't immediately become Haskell, even though people sometimes do call Typst scripting system functional. I don't think it's quite accurate, because there is this purity aspect to it, but I'm thinking about Typst as more of a deterministic Rust without references, which in my opinion is really a sweet spot in terms of language design. Let me show you what I mean. So if I have this snippet of Typst code, it doesn't really look functional, right? It's like a for loop, there's some mutation going on. I could rewrite this to JavaScript and it looks the same. And this is great for me because I like for loops, and I think most people find this a bit easier to work with than the purely functional approach. Yet, it does not cause any caching issues as long as it's contained in the function call. We can have local mutation, but it stays encapsulated. Whereas in JavaScript, nothing is encapsulated. Like, you have this, it's fine, but then someone can go ahead and write, oops, the numbers are modified here. And that's because in JavaScript, there isn't a clear concept of ownership. If we port this to Rust, then we'll suddenly see, or we can decide to make a mutable reference parameter here, an immutable reference parameter, or we can decide to move the value. And this has very different implications on what the caller can do. In the second example, the caller cannot mess, the function cannot mess with the data that the caller passed in, whereas in JavaScript, they could just scribble all over it. The references obviously have all this lifetime stuff that we don't want in a scripting language. And the vectors need lots of clones, but there is a way to spell this in Rust that retains the predictability benefits, but doesn't need lifetimes and is still reasonable performance, and that is basically this. And that is exactly what's happening in Typst, except for us merging these two allocations into one, because we can. And this also integrates perfectly with caching, because if we now return a vector and want to clone the result of our function into a cache, that's just an arc bump away. So in Typst, basically everything is arc all over the place, and it integrates nicely with caching. And just to close this chapter, it's still possible to have local mutation nicely, because you can look at this reference and see, is my arc unique? And if it is, you can just mutate it. And if it's not, then you clone it and then you mutate it, which is what this arc.makeMute function in the standard library does, which is a little gem, I think. And unlike JavaScript, which in my opinion are a nice spot, but at this point you may be thinking, like, what about that whole typesetting? Because I've been speaking about these nice function call semantics, and I kind of swept under the rug the whole typesetting thing, because we need heading numbering, right? And that is counting up. And LaTeX would just increment a counter at this point, but Typst cannot, because it's pure, all the functions are pure. And this is where we really get to the design part. And the question is, can we support counting and like other interactions in the document in a nice way without violating our purity constraints? And how would that stack up against the mutation-based approach? So if you've used LaTeX, you may know that it produces a bunch of files. And sometimes you need to run it again for the right thing to come out, or maybe even thrice. Or maybe you use LaTeX MK and then it does it for you, but it's still happening. Why is that? It's because documents are fundamentally interdependent. So, for example, let's take the example of a table of contents. So it's supposed to contain the headings and their page numbers. But like, how am I as the compiler supposed to know that stuff until I've laid out the document? I can just guess, and let's imagine this as being empty for now. And then after I've laid out the document, I can fill it in. So, okay, I put in the page numbers, and that caused it to grow from 2 pages to 3 pages, the table of contents. So it's still not right, and then I need to do it a 4th time, and now the heading numbers are finally correct. And all of this could happen in LaTeX, and then LaTeX MK will hopefully do 4 iterations. My point being that there is no way to solve mathematically for this. This is just, you have to retry until it stabilizes. And LaTeX does this by storing this information in temporary files. And like, for example, the TOC file, it stands for table of contents, and it contains just the table of contents stuff. And then it has another file for the references. So it uses it for table of contents, for cross-references. It does not use it for headings, though. You can just count up after all if you have mutation, right? But what I'm going to ask is heading numbering really that different? Because the table of contents needs to ask the question, which headings exist in the document? And the numbered heading needs to ask how many headings exist before me in the document. And these, at least to me, look like structurally very similar questions. Ultimately, like, we will not get around this whole retrying because you've seen the table of contents thing. So can't we try to make the whole thing principled within this pure framework and also implement counting like this? And this is what Typst introspection system is all about, making all of these interactions consistently possible in a coherent and like pure, consistent way. So Typst will recompile your document multiple times automatically until it stabilizes. It resolves all these kinds of cross-document interactions. And now we have again an interaction between like introspection and incremental, because most of the document is not going to change between these iterations, right? So we can reuse incremental compilation within a single clean compilation. So there's some sort of synergy here. And with this in mind, we want to see how this introspection system works in a bit more detail, because the purity also imposes constraints the other way around. And I'm going to do so specifically on the example of heading numbering, because it's like a visual example. So we have this question, how many headings exist before me in the document? So we can decompose that into 2 sub-problems. We have the problem which headings exist, which is, by the way, the same question that the table of contents asked. And we have the question, which of those am I? This question sounds a bit more abstract, but you'll see how this becomes relevant, and it's actually the much thornier problem of the 2. So let's start with a simple one. So in Typst, you can ask this question, which headings exist, by writing a query for the heading element. And to evaluate this snippet of Typst code, Typst will basically compile a document. We've seen this introspection loop, and conceptually it's just really passing the last document from the previous iteration to the current iteration. So the compile function takes this last document, and then it passes it through the whole call tree down to like where we evaluate our function calls. We still have this last document, and we can ask the document like what headings exist inside of you. But like the document is big, it's full of data, it changes all the time. Its hash also changes all the time. So we have again the problem that memorization is ineffective. But we've seen this, and the solution is the same. We just make the document tracked, we make the query function tracked, and now only function calls that actually depend on like queries in the document that themselves change will be reevaluated as we recompute these iterations. So it's always the same pattern with this track type. You have a type with a lot of information in it, you only care about a small part, you don't know statically which, but you can figure it out at runtime. So this solves the first problem. It's, as I said, it's not too big of a problem. But the second one, which of those headings am I? So take a look at this example here. We have a query for headings, and we ask, is the length greater than 0? So is there any heading in the document? And if yes, give me an outline, please. And then we have a heading, we have a section with another heading, and a third heading. Now, if we visualize the document's internal model, then initially, as observed by the first iteration, there's nothing, because we have no clue. And then after the first iteration, we have built this part of the document, because like we've seen this empty model. The query that you've seen will return nothing. It's empty. So the if will not evaluate to true. We have no table of contents. We have just this. Now we restart because it hasn't yet stabilized. So now we have 3 headings observed by iteration 2. And the if will now give yes. So we add a table of contents. And are we stable now? Not really, because now we have this 4th heading, so the heading query changes again. But now, okay, that's the next slide, but now it's stable because now the query, like whether it's 3 or 4, now it remains at 4. It's the same thing, it's stabilized. Now, with this in mind, recall the question of which heading am I? Because for a heading to number itself, it needs to resolve its heading numbering with the information from the last iteration. So to count how many headings are before me, it needs to do that with the information from the last iteration. So across these document iterations, we need to know which headings are the same. So we need some sort of unique identifier, basically. We could try and just count up. However, if you've seen, the document structure is evolving, so this won't really work because, for example, if I now remove this outline part of the tree, then the number assigned to A will already change, right? So we need something more stable. We could try hashes. What if we just take a hash of the element? But now we have sort of stability, but do we still have uniqueness? Because there could be multiple elements with the same data. We can have 2 headings with the contents A. We can have a hash collision here. Okay, let's try disambiguating these 2 by adding a disambiguation counter. And now we've actually got reasonable stability, and we have guaranteed uniqueness. And this was actually implemented at one point in Typst. But now we need mutable state across the whole compilation to produce these disambiguations. So the final evolution of this ID scheme is to take the hierarchy into account instead. So we can take the hashes of the parents, feed them into the hashes of the children, and we have this sort of hierarchical hashing scheme. We have nice compact IDs. It's just 128 bits. Like there's no vectors to track the parents. It's just hashes. And of course, we can still have the problem that among siblings, we have a collision because they have the same parent hash and the same data. But then we can use this disambiguation scheme locally within the neighborhood, but that's not like compilation-wide state, that's local state. So we have uniqueness, we have stability, and we have compilation-wide purity. And that's pretty nice. Now, it may seem like a very roundabout way of counting up because like we could count up before by just incrementing a counter. But the thing is, mutable state buys you that, it does, but it gives you not much more, honestly. Like any kind of interaction is just forwards. You can count up. But this means like the script evaluation order is now tied to the document order. You need to ensure that your script runs exactly as the document will be printed on the page. You can't look backwards. With Typst, you can just go and ask, like, what's the total number of headings? Like, the table of contents can ask, what's the heading number at this position in the document? Because it just needs to figure out the idea of that element, and then it can ask for all elements, find the number before that. So we can do all sorts of things. We can measure stuff, run code during that measurement, figure out the size of content. We don't care about which code runs. The code has no effects. We don't need to care about document order or anything in the code. It's very fearless. We can multi-thread, like willy-nilly. We can just cut the document in pieces, and we can still count up correctly. Like multi-threading in Typst, after I implemented this hierarchical hashing scheme, is literally just this. And as yet another effect, IDE tooling can give very nice suggestions. So this is an example I already showed 2 years ago, and this was 2 weeks of work to make this work. We have this YAML function that's parsing dynamically data, and the autocompletion can just show literally the data in the string, because everything can just fearlessly execute the code because there are no effects. Now, we also have this tooltip thing where you can ask, just by hovering a variable, what are the values, the concrete values at runtime. You can hover over the for loop and you'll see like the string that's being built. Like Typst has this scheme where it joins the strings in the for loop body, and you can see that. And all of that comes from this purity constraint that was motivated by live preview. If we didn't want live preview so badly, I don't think we would have any of this, because Typst functions probably wouldn't be pure. Now, even ignoring incremental compilation, Purity is a great fit for typesetting in my opinion, because the ability to have side effects just buys you so much less. I've been thinking about these problems for years now, and it did give me a few existential crises. These whole ID numbering schemes and stability and stuff. But both language design and also incremental compilation are just super fascinating topics, and after seeing the pieces of a good design come together, it's really rewarding. So I hope I've inspired some of you folks to build incremental software and to design for incrementality. Thank you.
Thank you very much, Lawrence, for that amazing talk. And also thanks for wrangling with all of the beasts and horrors that is typesetting so that we don't have to do it. Thank you very much. Any questions from the audience? There's one over here. We can also turn the light back up. Thank you. I don't know exactly if there will be a microphone being passed. No. Because of the record, remember?
Thank you for that talk. That was amazing. I'm very curious to hear a little bit more about the caching system, the memoization. So when something does change, like the user edits something, you need to recompute, part of that graph. Is that completely like pull-based, that you pull from? If you understand my question.
Like there isn't really a graph. Like if you're thinking in terms of something like Salsa and Rust Analyzer, there's this graph. There isn't any kind of graph. It's just really we call compile again. Compile calls its children functions, and if these are memoized, then it's memoized. Right. And yeah, so it's completely. Would you call that pull-based? I'm not sure, but
yeah, I would call that pull-based instead of like pushing through the graph.
Yeah, okay,
everything
yeah, it's
that depends.
I see it.
Yeah, that's really cool. And second question, just cache invalidation. Do you just throw away everything that wasn't used in the last iteration, or?
So what we currently do is you can ask for like how many iterations it should be live, and then we pick 10 in the CLI because you save from time to time, and then we pick 30 in the webpack because you type all the time. That's it. I mean, memory usage is a problem, and we'll have to figure something smarter out later, but it works.
Very cool.
So when you are recompiling, you're recompiling basically until you hit a fixed point, right?
Mm-hmm.
And is it possible with your system to have, say, like a heading that just bounces back and forth between two pages, and so you get a cycle? And
yeah.
So if it is possible, what do you do about that?
So ultimately, like in the general case, there is nothing we can do, I fear, because it's all Turing complete. Anything can happen. Like it could converge in iteration 5,264. We stop at 5 because like people have been asking me for a while to increase the limit, but I'm of the opinion that increasing the limit will just make packages worse because they don't have to care about reusing or doing as much work in as little iterations as possible. Like classically, the most feared warning you can get from Typst is layout didn't converge in 5 attempts. That's all you got. Last September, I implemented a system where it will tell you a bit more precisely what went wrong. And there's smarter things you could do. For example, like the thing you described where it oscillates between different states, you could detect oscillation because then you know it will not converge. We don't currently do that. We just tell you 5 iterations that didn't work. But yeah, you can be smarter, but you can't be completely smart, I fear.
As far as like the math and equations,
where?
Over here.
As
far as like the math and equation side of things, have you also sort of I know that there are changes to the syntax for that compared to LaTeX. Like, is that the same sort of ideology of designing it for this kind of incremental compilation or something else?
Equations are so small that it doesn't really matter. You can just recompute the whole equation. Like we just rely on the system to work, and it's fine. The equation changes are more motivated by the whole easy to learn thing.
One more over here.
Thank you. You said memory is a problem.
what exactly does that mean? Like, how much memory does it use, and how does it scale with document size?
I mean, depending on what you do, like if you use, the thing is, as I said, we cache all the user-defined functions, every function call. So if a package uses a lot of functions, then it uses a lot of memory because we don't do anything smart. We don't do inlining or avoiding caching. We will do that in the future. So it really depends on your document, but with a large document, you can easily get into the multiple gigabytes, and then, like, we will try to reduce that. It hasn't been the main priority so far.
Hello. Thank you for the great talk, and thank you for making Typst. I was kind of wondering what gave you the drive and the confidence to do this, because like making kind of a LaTeX replacement seems like a huge scope, and then to also improve all the things we hate about LaTeX seems like a huge task. So what kind of made you go through with this?
Yeah, so first of all, like I always was on the lookout for a project that could be a company, because that has been a dream of mine. And I felt like I was also always interested in programming languages. I tried to design a few like scripting languages before that, but I don't think, like I think it's much harder to make something people use, because programmers love programming languages, so they make programming languages, so there are a lot of them. Not a lot of people try this. The second thing is that I really, like the live preview thing was a strong motivator, because I felt it was possible and I wanted to make it work. And the third thing is that, like, I didn't do this alone, and it wouldn't have been possible. I would have given up 20 times over. So I'm not sure whether Martin is watching, but thank you, Martin. And to the rest of the team. So I think these would be the three things.
And we have one more question from the live stream, from the chat. The question is, will Typst collaborate with Pandoc project to create high quality conversions in the future?
So there has been a bit of, like, we've spoken a bit with some of the Pandoc maintainers. And right now Pandoc has done the amazing feat, honestly, like it's a bit naive, but also amazing that they have tried to implement a full front end for the Typst scripting language. It lags behind the Typst compiler, but it can do a lot. I suppose a more promising approach to really make it good down the road would be for Typst to assist, and to have basically Typst have a backend that emits Pandoc's IR in the same way that we export HTML. That could be done, and I'm open to it. Yeah, I think it will happen at some point, honestly.
Do we have more questions from the audience? The one at the back, okay. It's going to be a team effort to reach you. I hope it's a good question.
Yeah, thanks for making Typst. It's really nice. As someone who's built really nice tooling, if you had to do it all from scratch today, are there any things you would grab for, any crates or frameworks or things you do different?
Like rebuilding types from scratch, you mean? Like, I gotta admit, there is a bit of a not invented here syndrome going on at Typst. So, like, I like to have control. Like, for example, I looked into Salsa, and I think it could probably work for Typst, but I didn't figure it out, so I found it easier to do my own thing. But I wish there were some things that would be there, and maybe I haven't found them yet. Like, across all of these different integration points, like syntax highlighting is still not completely solved, I think, because syntax is sort of unmaintained. And yeah, Typst integrates so many different things. And for example, on the bibliography, we have our bibliography system, which is not yet completely baked. But I think what's nice to see is that there is some like shared foundational stuff growing. Like, for example, on the PDF side, we have more reuse with font crates, also with the stuff that Google has been building, and there's some stuff in Canva, so there's collaboration. I think that's much more important than picking some specific tool that would be nice to start from scratch.
All right, that was the final question. Another round of applause for Lawrence.
Thank you.
We have a very quick break to switch rooms if you like, if you dare. Other than that, we will be back at 17:05, so in 10 minutes. For the people coming in, please gravitate towards the middle. You can also, if possible, compact a bit. So maybe actually you all want to move over here because people come in here. So move to the left from your perspective. Have more space for other people. Thank you. And now for our second talk in this block, we have Adam Chalmers here from Zoo. He's a systems engineer there, and coincidentally also the second person in this room today to talk about a Rust-based DSL, which is really impressive. Previously, you worked at Cloudflare, if I'm not mistaken, and you're also one of the core maintainers of RV, which is a Rust-based Ruby language managers. Give it up for Adam.
Hello, thank you for coming. I'm really excited to be here. It's my first time in the Netherlands and my first time at Rust Week. Almost 6 months ago, I gave a little presentation at RustForge about a constraint solver I was starting to work on and about the things I was trying to learn there. And it's been almost 6 months now, and we've actually launched this constraint solver. So it's available. It's in Zoo, it's working, it is a success, and it's on crates.io if you want to use it right now. So I'm very happy to be able to show some of the lessons I've learned over the last 6 months of struggle. A little bit about me. Matthias already covered almost all of it. I'm also organizing austinsystems.org. So if any of you ever come to Central Texas and want to talk to a bunch of systems programming people, please do and come by. So the plan is going to be, we're going to talk about why I'm doing this in the first place, why we need a constraint solver. Then we'll figure out what a constraint solver actually is and how it solves the problem. We'll talk about how it works and how, in general, you implement them mathematically, and specifically how we've implemented ours in Rust. And we'll take a little step back and we'll think about what we all learned from this. So I work at Zoo. We're zoo.dev. We're a CAD suite. We're making new CAD software for the 21st century. This is a screenshot of our app. You can see you've got a view of the model on the right. And on the left, you have this funny little panel here with some little highlighted text. This is, the text is KCL. It's the KittyCAD programming language. This is how we define CAD models in code. But you don't have to write code. A lot of mechanical engineers don't ever want to write code, and they're right to. You know, they didn't train to be programmers. They trained to be mechanical engineers. So I think the interesting thing that Zoo does, you can use any way to edit your models. You can use a traditional point-and-click interface. As you click around in our interface, it'll generate the code for you, or you can write the code yourself manually by hand. And of course, these days, no one has to write code by hand if they don't want to, so we integrate with all kinds of ML and LLM agents and things. So I think having your choice of how you want to edit your CAD model is what separates us from the competition. You can write it yourself by hand, or using traditional point-and-click workflows, or code written by you or by a little agent. Zoo runs in the cloud, and we have an API you can use to configure your connection to us and send data. So this means that you don't have to be running your own CAD on your device. We can run on very fast GPUs and a very fast machine in the cloud. Or for enterprise customers who don't want to use the cloud, we can deploy it to your own infrastructure, and you get to have your own control and compliance and run it, in a legal place you like having it running and close to your users. So these are some things we've made with Zoo. We made a parametric telescope, a telescope where you put in the lens size you have access to, and the entire telescope will be redesigned to fit a lens that size. This is made by my friend Paul from work. So you can buy any lens you want, and because Zoo is inherently parametric, it has parameters. You put in a parameter like the lens size, and it'll reflow everything around that. This is one of the benefits of doing a code-based approach. It's very easy to put parameters into code. We make functions. Functions take parameters. Straightforward. We had a competition recently for making impressive stuff with Zoo. We had a little makeathon. This is my favorite model. It's a clavichord. This is an archaic instrument, and it was made by someone who kind of went and researched music theory from first principles about the physics of sound, and encoded the physical laws of sound in math in KCL, in our programming language. And so the code that you would use to kind of derive all the information is the same code that you use to make your model. So you have all the physical laws of sound encoded directly into your model. There's no need to kind of open up Python, figure out a bunch of numbers, and then go and do your CADing work. All the data is right there. And this is all available open source, and you can go and view it on our website or download the code yourself and read the very interesting write-up about how it works. The core gameplay loop of CAD, if it was a video game, would be that you are starting with sketching, where you make a 2D shape, like you'd sketch out a triangle or a square or something, some interesting shape. Then you make it 3D, maybe by extruding it. You kind of take the shape and you drag it up into the third dimension. Or you take your shape and you revolve it around the other axis to make a three-dimensional shape. Once you've made a 3D shape, you can then change it. You can modify it by filleting away a sharp edge, to kind of rounding off a sharp edge so it's easy to hold, or doing CSG operations, constructive solid geometry, 3D booleans, basically. You can take two existing 3D bodies and combine them by unioning them, or intersecting them, or subtracting one from the other, familiar operations. And once you've got your more complicated 3D shape, well, the shape is made up of many faces, and you can choose one of those faces, and you can start sketching on that face, and you can then do a new extrusion out from there. And so in this kind of generative process, you can build up more and more and more complex shapes. This is the kind of core game that CAD people are playing. Now, one of the problems with the first version of Zoo that we launched is in the sketch mode, where you do your 2D drawing. That's the very first thing, right? Sketching to create a 2D shape. Fundamental. we had some problems with our sketch mode. We had some problems that, I'm not going to get too scientific, but it did not meet expectations. The problem is that we had a very imperative sketch mode, right? We kind of assumed that people knew roughly what they wanted to do, and they would draw the lines in the right order. They'd start somewhere, they'd kind of draw lines and loop back to where they started, and boom, make a closed shape. That's not actually how mechanical engineers work. They don't like to do all the math beforehand and figure out exactly how long every line should be. We're using a computer. You should just make the computer do those calculations for you. No one should have to break out a pen and pencil and do any kind of trigonometry to figure out how long every side should be. So we had a lot of egg on our face with the first sketch mode, and we knew it was the first thing we had to fix up once we launched our 1.0. We've been working on that. The way that CAD usually works, you have a constraint solver. You might put some data together, like you would draw a rough kind of shape with maybe the right number of lines, then you go and add more information progressively to it. You'd say, I know these two lines should be parallel, and I know these two lines here should be the same length, and this angle here has to be a 90-degree angle. And by adding in more and more and more facts about the system, you should be able to see the computer filling in the blanks for you. Once you've had enough information, the computer can totally derive all the facts about your 2D shape for you. This is what a constraint solver does. It takes your partial information, lets you add more facts in, and fills in the blanks for you. Existing constraint solvers were not really going to work for us. We either had to pay a lot of money for them, or if we wanted to use one of the free ones, we would not be able to charge any money. And making a full production-grade CAD app that can be used to actually make real things like cars and planes, it takes a lot of programmers to make that, which means we have to pay a lot of programmers' salaries, which means we need to make money ourselves. So we couldn't find anything that was going to be free and open source, so we did it ourselves. We're releasing it. It's called Easy Peasy. It's up on docs.rs, it's on crates.io, it's everywhere you get good Rust code. The name Easy Peasy is ironic. It was not, in fact, easy. This is something I've been noticing in my self-work. I would say things are easy, and then kind of find myself down a big, deep rabbit hole. Like in this case, I had a little syntax error where my language was not flexible enough to do computation inside the array index. So, we should fix that. And then that afternoon, I got a request for an update. It was not going super well. And by the next morning, I was happy to say, okay, actually, I should really stop using the phrase easy peasy. So the name is ironic. It was very hard. I'm very excited to make this open source. I've always just done kind of work for, big or small tech companies and closed systems, and maybe we'd open source some stuff for that's had thousands and thousands of engineering hours put into it. So this is, my little way of giving back, and yeah, I love this open source world, and I'm excited to finally have something that maybe might be worth other people using. So what is it? What have we actually built? Let's do a little demo of it. We're doing a live demo of streaming stuff on conference Wi-Fi, so let's just hope this goes well. This is Zoo Design Studio. This is the app we make. We're going to start a sketch. We choose a plane to start sketching on. And let's add in some lines. We're going to add in some lines here. Yeah, we'll make like a quadrilateral or something. Cool. And now I'm going to select some lines. I'm going to apply a constraint to it. I'm going to hit E for equal. Now these lines have the same length. And if I try to move one of these points around, it's going to keep those two lines the same length. If you lose track of which lines you're talking about, you can mouse over one. You can see all the constraints on it. So I'm going to mouse over the equal sign, and you see that it's going to highlight the other constraints. If I want to say that these two lines are equal as well, or I can say that they're going to be parallel maybe, so I'll make them parallel, and then we get the same nice mousing over. You can apply dimensions, which is a CAD mechanical engineer way of saying give a fixed length. I'm going to dimension this to be, its current length is 10.01. I think I'm going to make it, 4 millimeters long instead. And then the dimensions will kind of stay there, and you can see what's going on. Right now it's blue because we have not fully constrained everything. There's still degrees of freedom left in our system. I'm going to select the origin and this point here, and I'm going to make them coincident. And then we have additionally constrained it more. And as I add more and more and more constraints, it'll eventually turn white. Let's make this fully constrained, and then we'll say that this has to be vertical or horizontal maybe. Yeah, done something silly. Yeah, I'm not actually a mechanical engineer, as you can tell. Yeah, here's one I made earlier. Here's a fully constrained sketch with all the dimensions put in. There are no more degrees of freedom left. So if I mouse over everything, I can see all the constraints being made, and I cannot drag it around anymore. It's totally locked into place. This is generally the desirable end state for a sketch. You kind of draw an approximation, and then you add in more information until the sketch turns white. And then you know you've done a good job. Your initial guesses that were kind of just gut feeling no longer have anything to do with the final sketch. All the information is fully defined. And as you could see, when I'm clicking around, I'm going to, maybe I'll start a new sketch somewhere. When I'm clicking around, you can see more syntax being added on the left. So even if you don't want to look at the code, if you open it up, you can kind of see what it's doing because you can couple the code generation to the UI interaction. I think this is the novel thing about Zoo. There are other ways to use code to make CAD models. There are other ways to use a point-and-click interface to make CAD models. But I think only Zoo right now lets you use both of them. They are not two separate worlds. They are joined together. OK, live demo was successful. No, we don't need to play the backup. There we go. So we saw that the sketch mode, you click around in the UI inserts lines of KCL. KCL is our little language, and it has an abstract syntax tree, which we then execute. Easy peasy is the constraint solver library. When KCL sees a sketch block like this, you see this sketch on the plane, like XY. We then apply a bunch of constraints here in geometry, and when you finish up the sketch block, it evaluates them all and produces the final answer. So what does Easy Peasy actually do? It's a library. You can download it now. It's got entities like points and lines and circles. These are geometric entities. They have some properties, like a line has a start and an end, and a circle has a radius in the center. You give some initial guesses to these properties. In the UI, when you're inserting them, we use the UI clicking as the initial guesses. You could do this in a pure code way. We have a CLI that you can use to execute KCL programs. And at that point, you're kind of making up some guess numbers. You can then take these entities and apply constraints to them. There's two kinds of constraints. We have what's called dimensional, where you put a constraint on the property, like a radius or the position. And there's geometric, which are about relationships, like these two lines have an equal length, or this line is tangent to this circle. Once you've got your entities and your constraints, you can solve it. What is solving it? You're kind of saying, what are all the properties of my shapes? Give me specific concrete values such that all the constraints are satisfied, if possible. You might not be able to satisfy them all. You may have conflicting constraints. That's okay. That's part of life. That's part of the drafting process. That shouldn't blow up in your face. If you can't find a solution, if a solution's impossible, we should give you a pretty good solution. We should do our best effort. In practice means we try to give you a least square error solution. And if it's not possible, we should show you why. We should highlight and show you which constraints couldn't be solved in red, so you get, blue for under-constrained, red for over-constrained. Ideally, everything turns white and it's perfectly constrained, but that's really up to you, the user. Let's talk about math. I last took linear algebra, I think, in 2011, which, goodness, it's been a long time now. So I had a lot to relearn. A constraint is basically a mathematical equation. Let's take the example that 2 points are vertical, or the line between these 2 points is vertical. You can think of this as an equivalence. It's saying that the first point's x is the second point's x. They're equal to each other. You can also rearrange that equation. Instead of saying that point 1's x is equal to this other point's x, you can say the difference between their x's should be 0. Now, this is trivial math to do the reordering, but it's really helpful to think about this with 0 on the right-hand side, because that means the left-hand side gives you a measure of how close your constraint is to being satisfied. We call this the residual, the amount of error, basically. So the left-hand side is big, means you are doing a bad job of satisfying the constraint. And if you can measure how far away you are from satisfying it, you then know if you're making progress. So the system of constraints you have is a simultaneous equation system. In this example, we'll look at a little toy system and how you solve it. Let's say we've got 2 points P and Q. P is fixed to the origin. Q is somewhere on the x-axis. And the line PQ is going to be vertical. This means we've got 4 equations, really. Px is 0, Py is 0, Qy is 0, and Px equals Qx. Very simple example. Let's reorder these. We're not going to just have 4 random equations. We're going to make sure they're all in the forms we need, all residual equations with 0 on the right-hand side. Now let's take a look about how we actually solve that. How does this work? We have 4 variables in our system, px, py, qx, qy. We have 4 equations. We can view each of these as being one residual equation with a little f. Little f means one constraint residual. And big F is the sum of all the little f's. We want to minimize big F by minimizing all of the little f's. Minimize the total error in our system by making sure each constraint is solved, basically. So how do we solve a system of simultaneous equations like this? I kind of picture each equation or each variable as like being a little dial you can adjust. And this big F is made by combining all these little dials in just the right way. It's like a big complicated machine, and you're trying to get some output, and you just have to kind of twiddle the dials until you get it all right. And it's not really clear how, so you just kind of, you twiddle it, and you see, did the big F go up or down? You twiddle another one. That kind of random approach works eventually, but it takes a hell of a long time. So instead, we actually have a lot more information. We can look at the partial derivatives. We can differentiate each of these equations, and that tells you how much they go up or down as you make each little variable go up and down. If you wiggle the dial for each variable, how much does it affect the overall total F? So we've taken our 4 equations, and we're going to differentiate them all. We're going to take the partial derivative for px, py, qx, and qy, because there's 4 ways to differentiate this, because there's 4 variables. When you differentiate this px equals 0, as you adjust px by 1, this equation will go up by 1, because that's all there is to it. In this equation down here, equation 4, if you make px bigger, the equation right-hand side gets bigger. If you make qx bigger, the equation right-hand side becomes smaller, gets negative. So we differentiate for each of these variables. Now, if you use the power of your imagination, you can look at this table with 4 vectors, each of length 4, and if you really concentrate and visualize, you could just imagine this being a single 2D grid with 4 columns and 4 rows. I know it's difficult, so if you can't do that, don't feel bad. I've prepared a visual aid over here. This is basically taking a series of vectors and stack them together to make a matrix. And this matrix is called the Jacobian. If you've taken linear algebra more recently than me, you may recognize this, but it was new to me. Basically, every column here represents a variable, and every row here represents one of the equations. So this Jacobian is what we need to solve this system in a reasonable amount of time. We can use something called the Newton-Gauss method. We take the residuals in the Jacobian matrix, and the matrix tells us how much to adjust each variable to minimize the residuals. Now, this all works fine if your residuals are all totally linear, if you can predict perfectly how much adding up one of the variables will do. But many of these constraints are non-linear. So take this little parabola here. If it does this linear algebra and arranges everything, and we call out to fair to actually matrix calculation. This is nice because we could change fair out for a different linear algebra library, or we could add constraints without needing to worry about fair at all. All the different pieces are quite nicely isolated. Constraints look like this. We just have a big enum of all the constraints. We know all these constraints ahead of time. We can't put in an arbitrary equation. And this means we lose a little bit of flexibility, but it's okay because you can't really do like arbitrary equations in CAD. We're fundamentally manipulating a known set of entities with a known set of operations to apply to them. This means we can do all the differentiation ahead of time. This is really helpful because we don't have to then do that differentiation while the code is running. So it makes it much faster. The constraints have a number of residual equations, the residual equation themselves. We need to know which variables could affect the partial derivative and the partial derivatives themselves. I already mentioned this stuff. I'm not very good at math, doing math by hand. I tried to do all the differentiation ahead of time, and then I had to copy the math from my paper notes into code. It doesn't really work. Instead, I use a library called SymPy. SymPy is nice because it's kind of everyone knows a little bit of Python. It's a good language for collaborating with your data people, and everyone can pick up a little bit of Python. It's nicer than having to teach your whole team Rust. SymPy lets you have this really nice high-level abstract representation of equations. But you can actually generate Rust code from SymPy. You can tell SymPy, hey, take this symbolic equation and give me the Rust code that corresponds to it. This is awesome. This is so helpful. I could just copy and paste the Rust code directly into my source code, and I knew that it was valid because it came from a totally reproducible artifact. I can add the SymPy into my repo and have it just output stuff. So how did it go? How do we test it, firstly? I made a little DSL for defining test cases so we could easily put in handpicked test cases and make sure they turned out correctly. This is okay, but handpicked test cases have a way of not really covering everything you need to. So we use property testing heavily here. We do something like say you take 2 random points in the plane and you make a distance constraint between them and then you solve it. And then afterwards, those 2 points should be the given distance away. You can choose any 2 positions and any distance and it should do that. So it's a great use case for property-based testing. I use cargo mutants, which will basically look through your code, look at every line, and just fuck it up real bad. It'll just comment it out or make it return 0 or ignore it somehow, and it checks that the test broke. If no test broke when you messed up your code, then you are missing some test coverage. It's really effective. It does take a long time to run, so I would just run it overnight and see what it came up with. And we also visualize the residuals. This is a image showing how, say you've got 2 points we're going to make coincident, the green point and the red point. These lines are showing the amount of error. If you put the red point here, you'd have like 10 units of error. Here you have 20 units of error. And this helps us verify that our residuals are reasonable. So we take these images, we generate these images, and we write them to disk. And we use a library we made at work called 2020 to get a kind of fuzzy match and make sure that all the pixels look roughly correct. And that way we make sure that when we change our math, we always have like an accurate generation of the visuals of the math on the disk. This is basically like cargo insta, but for images. Performance. We need to make this fast because we need to run this every time the user drags a point around. Our goal is to have like a system of 500 variables. That's what our mechanical engineers said would be like a large, but occasionally you'd see it system. And we want to do it smoothly at 60 solves per second as the user moves the mouse around. Fair is very fast. It supports SIMD, and it can handle both sparse and dense matrices. If you can think about a matrix, it's got a lot of columns, a lot of rows. In our use case, almost all of those cells are going to have 0 in them for the partial derivatives, because even if you have 500 different lines, most constraints will only talk about 1 or 2 of those lines, maybe 3 or 4. Most of the matrix will be empty. So you really don't want to be calculating all these zeros and adding up all these zeros. So it's important to have a sparse matrix library. We're running this in Wasm as well, and so I was a little bit concerned about the performance, but it turns out that there's only a roughly 3.7x slowdown when you run in Wasm. I suspect this is because Fair uses SIMD very heavily, and on my MacBook, I can do 8 simultaneous F64 operations, but in Wasm you can only do 2. So that suspicious kind of 4x ratio is probably where the slowdown happens, I think. And if we ever need more performance, we can always send the code up to the server, run it on our x86 servers with higher SIMD. I was impressed that SIMD supports, that SIMD is in Wasm, and that Fair just natively supports it somehow. The maintainer Sarah didn't know that would happen. It's being put in there by LLVM automatically. If you want to check if your Wasm uses SIMD, you can look up all the Wasm instructions in a website linked in the slides, and then you can look for specific Wasm opcodes in the Wasm opcode explorer. So you upload your binary to this little website, and it just scans it and gives you all the opcodes, and you can just look up, hey, are there any SIMD operations here? So that's helpful for checking if LLVM has properly auto-vectorized it for you. The performance was pretty good, but it wasn't up to where I wanted it to be. So I spoke to one of our other engineers. See this dense matrix and this sparse matrix representation of the same matrix. I said it was really important to have a sparse matrix. There are some problems that people generally run into when they're doing linear algebra heavy code. There's 4 classic mistakes people make. You maybe get the matrix the wrong way around, your columns and rows get swapped, or you make something dense that should be sparse, or you have to square something or square root it for the math to work out. I've made all of these mistakes so far in this project. So I was putting all of my zeros into the sparse matrix. So I got all the downsides of a sparse matrix and all the downsides of a dense matrix together. Obviously, as you can see here, it's much faster when you stop being stupid. Someone said, if you make your code 2 times faster, you've done something smart. If you make it 10,000 times faster, you've just stopped doing something stupid. That's exactly what happened here. I'm very happy with the results. We are well above our 60 solves per second, and the architecture is very straightforward. We can easily add new constraints in without worrying about changing anything else. We have a lot of work to do in the future. We're still tweaking our residuals and finding new, smoother ways to solve things. We'd like to add in more geometry, like ellipses and Bezier curves. Our UI integration, can always be improved. And I'm really excited because we're going to add 3D support soon. It's really important in CAD that you can position objects in a 3D space, like say, these two parts should be pressed up against each other, or this part with a hole should match up with this part with a hole so I can put a bolt through them together. So easy peasy 3D coming soon. In the last couple of minutes, let's just talk about AI real quick. Is anyone else here kind of feeling a bit weird about all the AI? I've had a lot of chats with people here at this conference about AI, and a lot of these chats have started with, oh, thank God, because I didn't want to bring it up, because like everyone is going so crazy about it in every direction. I don't think that's going to be very healthy for this community long term. I think we've got to start talking about this stuff a little bit more. I know it's kind of scary because we have so many intense opinions in every direction, but I think most people here are pretty cool, good people, and I'd much rather talk about it with you than have the AI conversation be dominated by some of the worst people on the planet. So let's maybe try to turn down the conversation temperature a little bit. Here's how I've been using AI for this. I've been seeing a lot of projects online, and my first thought is like, did you actually do this, or was this all just AI code gen? Like, I think it's good to be honest about what you're using it for. I didn't use AI for this a whole heap, but I tried to use it in ways that made sense. I got code review from Codex as a way to kind of see if I could catch obvious mistakes before having to make my coworkers be like, oh, you missed the sign here. That kind of like lossy pass. It's not going to catch everything, but if I can reduce the burden I'm putting on my coworkers and asking them for review, that's worth it to me. It's pretty good at explaining linear algebra because we've had like centuries of people writing about it, so it's got a lot of data to draw on. It's good for explaining some concepts. You know, you can always go and back them up later. And prototyping some of the more complicated constraints as well. None of those prototypes made it into production because they were kind of useful for me to get a basic idea and see, okay, how does this really work? But we basically did not like the output, did not trust the output, and I had a really good human to collaborate with. But it was good to have a basic prototype at the start. It was an actual prototype, not like I think we've all had PMs who were like, oh yeah, we'll put a little prototype, and then you actually get shoved into production. So basically, all this stuff was mostly done by hand. I used it to have like a little bit of like a sanity check for stuff. This is probably the hardest thing I've done in a very long time. I was very nervous when I started this project. I really did not understand the math behind it. I figured we have to hire someone who was an expert in this kind of stuff, but by talking to my coworkers and taking some time, like giving myself enough time to really do some research, it wound up going pretty well. I would like to be the best programmer I can be. I don't want to let an AI do stuff for me. I'd rather have an AI like help me be a better programmer, like help me be more rigorous or help teach me how to do something. I'd much rather that than try and give the hard parts to someone else, whether they're a human or a bot or something else. Ideally, I'd like to be the best programmer in the world, but Alice Rill already exists and I can't be her, so that's okay. I'd rather just settle for like getting a little bit better at this every day. So yeah, that's what I've done. I'm really thankful for the people at Zoo and former Zoo people who helped me along the way. I got a lot of good research from people. There's some really good papers out there online because a lot of people are solving a very similar problem or the same problem in a different way, something like that. And thank you so much. We are hiring, but for various legal reasons, we really want to hire people who are already based in the USA. So I'm guessing that's not a lot of people in this crowd, but feel free to tell your friends about it. Thank you so much.
Thanks a lot, Adam. That wasn't easy peasy at all. So thanks for going through the troubles. And we have time for maybe 2 questions. We can, raise your hand if you have any question. We have one here. Over there we have one and one more. We might not have time for all of them. I'm gonna pass the mic around. You were the first to raise your hand.
Yeah, so just a quick question. When you let the user drag the points around, does that become like another type of constraint? Like, oh, we want to like iterate on the current positions, so like move them not a lot. Is that?
Yeah, the way we actually do that is when you drag the mouse, we add a kind of temporary constraint to fix that point at that location. And then when we solve it, we remove that constraint afterwards and we write that final value back as the initial guess in the code. So this way, the mouse constraint is not, it's like a lower priority constraint because while you're dragging it around, we want to take it seriously. And then when you let go, we kind of snap into place to the closest solution to that.
Okay, yeah, that makes sense.
Thank you.
One more question. One over here.
Thanks for the talk. Did you consider incremental solving as well, or are you just doing the entire solve each frame?
We considered the incremental solving. I was almost a little disappointed. You know, there's all this great theory and literature about how to make all these interesting optimizations. You know, you can take your system and you can decompose it into smaller parts and solve them independently. And it's just been fast enough doing the basic naive thing. I think that because we've put like 10% of the global GDP every year goes into making matrix multiplication faster, at this point, matrix multiplication is really, really fast. So all those old papers from when matrix multiplication was slow, you can just do stupid shit these days, and it works because CPUs are really, really fast. And a lot of these systems, you know, if you're doing complicated NVIDIA grade, you know, you're doing 3D rendering in a complicated, you know, super ultra realistic environment, and you've got bajillion pixels and polygons and things. We're not doing realistic real world kind of simulation. This is for this is to make a shape, you know? And so the systems we consider large are puny by the capabilities of modern hardware. I'd love to have the chance to do more of that stuff in the future, so we'll see.
Thank you very much, Adam. We are now closing the conference, and before we do that, I would like to thank everyone and also send you to Cinema 12 for a closing event, especially the speakers, also you, Adam. And this will be at the main track. Thanks everyone for being part of Rust Week. I think it was an amazing conference and hope to see you all back next year.
Thank you. At the end of that event after. Yeah.